1. Introduction to Delaunay Triangulation. 1.1 Overview of Delaunay Triangulation. Delaunay triangulation is a fundamental concept in computational geometry and is widely used in various applications, particularly in 2D graphics. This section provides an overview of Delaunay triangulation, explaining its definition, characteristics, and significance in graphics programming. Delaunay triangulation is a geometric technique used to partition a set of points in a plane into non-overlapping triangles. It ensures that the triangulation satisfies the Delaunay condition, which states that no point should lie inside the circumcircle of any triangle in the triangulation. This property guarantees the optimality and uniqueness of the triangulation, making it a widely adopted approach for many geometric operations and computations. The Delaunay triangulation has several important characteristics that make it desirable for various applications. First and foremost, it maximizes the minimum angle among all the triangles in the triangulation, resulting in well-shaped triangles with minimal distortion. This property is highly beneficial in many graphics applications, as it produces visually pleasing and well-behaved meshes. Another characteristic of Delaunay triangulation is that it minimizes the number of long and thin triangles, which can negatively affect the accuracy and stability of geometric computations. Delaunay triangulation aims to create triangles that are as equilateral as possible, ensuring a better distribution of triangle aspect ratios. This aspect makes it particularly useful in graphics applications such as mesh generation, image warping, and terrain modeling. Delaunay triangulation is also known for its locality property, meaning that any vertex in the triangulation is connected to only a subset of other nearby vertices. This property allows for efficient local updates, making it suitable for dynamic applications where the point set changes over time. In addition to being widely used in computer graphics, Delaunay triangulation finds applications in various other domains. It plays a crucial role in computational physics, where it is used for particle simulations, finite element analysis, and mesh generation for physical simulations. It is also used in geographic information systems (GIS), where it helps in the creation of TIN, triangulated irregular network models, terrain analysis, and contouring. Moreover, Delaunay triangulation is employed in computer vision for feature extraction, image registration, and image morphing. Several algorithms have been developed to compute Delaunay triangulation efficiently. These algorithms can be categorized into different types based on their approach, such as divide and conquer, incremental, and sweep line algorithms. Each algorithm has its own set of advantages and disadvantages, depending on the specific requirements and constraints of the application. The choice of the algorithm depends on factors like time complexity, space complexity, and the desired level of robustness. Understanding the advantages and disadvantages of Delaunay triangulation is essential for choosing the appropriate algorithm for a specific scenario. While Delaunay triangulation provides many benefits, such as good triangle quality and locality, it also has certain limitations. For example, it can be computationally expensive for large datasets, and the resulting triangulation may not be suitable for all applications due to the inherent constraints of the technique. In the following sections, we will explore the various applications of Delaunay triangulation and delve deeper into different types of algorithms used for its computation. We will also discuss the advantages and disadvantages of Delaunay triangulation in more detail, providing insights into its practical implementation in 2D graphics using the C programming language. 1.2 Applications of Delaunay triangulation. Delaunay triangulation is a fundamental technique used in various fields of computer science and engineering. Its versatility and efficiency make it widely applicable in a variety of applications. In this section, we will explore some of the key areas where Delaunay triangulation finds practical use. 1.2.1 Computer graphics and animation. One of the primary applications of Delaunay triangulation is in computer graphics and animation. It is used to create smooth and visually appealing 2D and 3D meshes that serve as the basis for rendering realistic objects and scenes. By triangulating a set of points representing the vertices of the object, Delaunay triangulation helps create a mesh that adheres to certain geometric properties, such as maximizing the minimum angle of the triangles. This ensures that the mesh maintains an optimal shape and avoids distortions. Additionally, Delaunay triangulation is utilized in texture mapping, where images or textures are mapped onto the surface of a 3D object. The triangulation helps determine the appropriate placement and distortion of textures on the object's surface, resulting in accurate and realistic texture rendering. 1.2.2 Computational geometry. Delaunay triangulation serves as a fundamental building block in computational geometry, a field that deals with the analysis and manipulation of geometric objects. It is used in various computational geometry algorithms to solve problems such as nearest neighbor search, convex hull construction, and Voronoi diagram generation. For example, in nearest neighbor search, where the goal is to find the closest points to a given query point, Delaunay triangulation is often employed to efficiently partition the search space and perform quick search operations. In convex hull construction, which involves finding the smallest convex polygon that encloses a given set of points, Delaunay triangulation plays a crucial role. The edges of the Delaunay triangulation form the boundary of the convex hull, leading to an efficient and accurate convex hull construction algorithm. 1.2.3 Finite element analysis. Delaunay triangulation is widely used in finite element analysis, phi, a numerical method for solving partial differential equations governing various physical phenomena. In phi, the domain is divided into smaller finite elements, and the equations are solved on these elements to approximate the behavior of the system under study. Delaunay triangulation is employed to generate a mesh that discretizes the domain. The quality of the mesh is critical in phi as it affects the accuracy and convergence of the numerical solution. The use of Delaunay triangulation ensures that the resulting mesh has well-shaped elements, minimizing distortion and improving the accuracy of the finite element analysis. 1.2.4 Geographic Information Systems (GIS). Geographic Information Systems (GIS) involve the storage, analysis, and visualization of geospatial data. Delaunay triangulation plays a vital role in various GIS applications, including terrain modeling, interpolation, and network analysis. In terrain modeling, Delaunay triangulation is used to generate a TIN, triangulated irregular network, which represents the terrain as a set of triangles. This allows for efficient storage and analysis of elevation data. Delaunay triangulation is also utilized in the interpolation of data points to estimate values at unobserved locations on a map, such as estimating the height or temperature at a specific location based on nearby measurements. Furthermore, Delaunay triangulation helps in network analysis by representing and analyzing the connectivity between spatial features, such as road networks, river networks, or telecommunication networks. 1.2.5 Computational Physics and Mesh Generation. Delaunay triangulation finds considerable application in computational physics for simulating physical phenomena. It is used to generate meshes in numerical simulations, providing a discretized representation of the physical domain. These meshes help approximate the equations governing the physical system, enabling the simulation of fluid flow, structural analysis, and other physical processes. Additionally, Delaunay triangulation is employed in mesh generation algorithms to create well-balanced and efficient meshes for simulations. These meshes must satisfy certain criteria, such as conforming to boundaries, maintaining element quality, and adapting to the solution. Delaunay triangulation algorithms offer efficient ways to generate high-quality meshes that satisfy these requirements. Overall, these applications demonstrate the broad utility of Delaunay triangulation in computer graphics, computational geometry, finite element analysis, geographic information systems, computational physics, and more. The ability to efficiently and accurately triangulate points in 2D space makes Delaunay triangulation an essential technique in various fields of study and research. 1.3 Types of Delaunay triangulation algorithms. There are several different algorithms available for implementing Delaunay triangulation in 2D graphics using C. Each algorithm has its own advantages and disadvantages, and the choice of which algorithm to use depends on various factors such as the nature of the input data, the desired performance, and the specific requirements of the application. 1.3.1 Incremental Algorithm. The incremental algorithm is one of the most common and widely used approaches for implementing Delaunay triangulation. This algorithm starts with an initial triangulation and adds points incrementally to the triangulation, ensuring that the Delaunay property is maintained at each step. The incremental algorithm has a time complexity of O(n squared, where n is the total number of points in the input. The incremental algorithm is relatively easy to implement and understand compared to other algorithms. It is also memory efficient since it only requires storing information about the current triangulation. However, one drawback of this algorithm is that it can be sensitive to the order of point insertions, which may affect the quality of the resulting triangulation. Additionally, the incremental algorithm may not be suitable for handling large data sets due to its quadratic time complexity. 1.3.2 Bowyer-Watson Algorithm. The Bowyer-Watson algorithm is another popular method for implementing Delaunay triangulation. This algorithm uses a divide and conquer approach to construct the triangulation. The basic idea is to recursively partition the input points into smaller subproblems, triangulate each subproblem independently, and then merge the subproblems together to obtain the final triangulation. The Bowyer-Watson algorithm has an average time complexity of O(n log n, which makes it more efficient than the incremental algorithm for large data sets. The Bowyer-Watson algorithm has the advantage of producing high-quality triangulations since it is less sensitive to the order of point insertions compared to the incremental algorithm. However, the recursive nature of this algorithm can lead to stack overflow issues when dealing with extremely large datasets or in the presence of degenerate cases. To mitigate this problem, one can use techniques such as iterative or adaptive refinement. 1.3.3 Sweep Line Algorithm. The sweep line algorithm is another efficient approach for implementing Delaunay triangulation. This algorithm utilizes a line sweeping technique to construct the triangulation. It starts by sorting the input points in a specific order, typically based on their x-coordinate. Then, a sweep line is moved from left to right, maintaining a current status of the triangulation as it sweeps across the points. The sweep line algorithm has a time complexity of O(n log n, making it suitable for large datasets. One advantage of the sweep line algorithm is that it can handle certain degenerate cases, such as collinear points or cases where multiple points have the same x-coordinate. However, the sweep line algorithm is more complex to implement compared to the incremental or Bowyer-Watson algorithms. It requires the use of efficient data structures, such as a balanced binary search tree or a priority queue, to efficiently handle insertions, deletions, and lookups during the sweeping process. 1.3.4 Alternatives and variations. In addition to the aforementioned algorithms, there are other variations and alternatives for implementing Delaunay triangulation in 2D graphics using C. Some of these include divide and conquer algorithms with spatial partitioning techniques, randomized incremental algorithms, and hybrid algorithms that combine different approaches. The choice of algorithm depends on various factors such as the specific requirements of the application, the size of the input data, the desired runtime performance, and the available computational resources. It is important to carefully evaluate the pros and cons of each algorithm and select the most appropriate one based on the specific needs of the project. In the next section, we will explore the advantages and disadvantages of Delaunay triangulation as a technique for solving geometric problems in computer graphics applications. Note: throughout the book, we will focus on the incremental algorithm as it provides a good balance between simplicity and efficiency for most practical applications. However, the concepts and techniques discussed can be applied to other algorithms as well. 1.4 Advantages and disadvantages of Delaunay triangulation. Delaunay triangulation is a widely used technique in 2D graphics and computational geometry for various applications. Like any algorithm or technique, Delaunay triangulation has its own set of advantages and disadvantages. In this section, we will explore the benefits and limitations of using Delaunay triangulation in 2D graphics. 1.4.1 Advantages 1. Flexibility and adaptability. Delaunay triangulation is a highly flexible technique that can be applied to various types of geometric data. It works well with both regular and irregular point sets, making it suitable for a wide range of applications. It can handle both dense and sparse point distributions, ensuring reliable triangulation results regardless of the density of the points. 2. Optimality. One of the most significant advantages of Delaunay triangulation is its optimality. The Delaunay triangulation maximizes the minimum interior angle of the triangles, resulting in triangles that are as close to equilateral as possible. This property guarantees the creation of high-quality triangles that are well suited for various computations and simulations. 3. Robustness. Delaunay triangulation is a robust technique that can handle various edge cases and geometric scenarios without any issues. It can handle degenerate cases, such as collinear points and points that lie on the boundary or inside the convex hull, ensuring accurate and reliable triangulations in challenging situations. The robustness of Delaunay triangulation makes it a suitable choice for real-world applications where input data can be unpredictable. 4. Locality preserving. Another advantage of Delaunay triangulation is its ability to preserve the local properties of the input data. It ensures that each triangle in the triangulation only connects neighboring points, resulting in a representation that accurately reflects the local connectivity of the input points. This locality-preserving property is particularly advantageous for applications where understanding the local relationships between points is essential, such as terrain modeling or path planning. 5. Computational efficiency. Delaunay triangulation algorithms, such as the incremental algorithm or the sweep line algorithm, have been extensively studied and optimized over the years. As a result, efficient implementations of these algorithms can triangulate large point sets in a reasonable amount of time. This computational efficiency is crucial for real-time applications and interactive graphics, where triangulation needs to be performed quickly to provide smooth and responsive user experiences. 1.4.2 Disadvantages 1. Memory consumption. Delaunay triangulation requires the storage of additional data structures, such as point lists, triangle lists, and edge lists. The memory consumption of these data structures can become a limiting factor, especially when dealing with large datasets. The space complexity of Delaunay triangulation is linear or near-linear, depending on the specific algorithm and implementation, which means that memory usage can grow significantly with the size of the input. 2. Preprocessing overhead. To perform Delaunay triangulation, preprocessing steps are often required, such as sorting the input points or constructing an initial super triangle. These preprocessing steps can introduce additional computational overhead, especially for algorithms with higher time complexity. In some cases, the preprocessing steps can dominate the overall runtime of the triangulation process, making it less suitable for scenarios where real-time performance is crucial. 3. Edge cases and degenerate inputs. While Delaunay triangulation is robust in handling various edge cases and degenerate inputs, there are still scenarios where it may produce undesirable results. For example, in cases where the input points lie on a straight line or very close to each other, the resulting triangulation may have long and skinny triangles that can lead to numerical instability or inaccurate computations. It is essential to handle these edge cases carefully and consider alternative approaches when necessary. 4. Difficulty in parallelization. Parallelizing Delaunay triangulation algorithms can be challenging due to the inherent dependencies and data structures used in the process. While there are parallel versions of some algorithms available, achieving efficient parallelization and load balancing can be non-trivial. This limitation can restrict the scalability of Delaunay triangulation in multi-core or distributed computing environments. 5. Practical implementation complexity. Implementing Delaunay triangulation algorithms in practice can be complex, especially for beginners or developers who are not familiar with computational geometry concepts. The algorithms involve intricate data structures, geometric calculations, and edge flipping operations, which require careful implementation and rigorous testing. However, various libraries and resources are available to simplify the process and provide ready-to-use solutions. In conclusion, Delaunay triangulation offers numerous advantages, including flexibility, optimality, robustness, locality preservation, and computational efficiency. However, it also has some limitations, such as memory consumption, preprocessing overhead, challenges with edge cases and degenerate inputs, difficulty in parallelization, and practical implementation complexity. Understanding these advantages and disadvantages is essential for choosing the appropriate triangulation technique for specific applications and considering potential trade-offs. 2. Basic concepts of 2D graphics. 2.1 Coordinates and coordinate systems. In any graphics system, understanding coordinates and coordinate systems is essential for working with 2D graphics, including implementing Delaunay triangulation. Coordinates define the position of a point on a plane, and a coordinate system provides the framework for defining and interpreting these positions. Cartesian coordinate system. The most commonly used coordinate system in 2D graphics is the Cartesian coordinate system. In the Cartesian system, a 2D plane is divided into 4 quadrants containing points with positive and negative x and y coordinates. The origin, denoted as 0, 0, serves as the reference point from which all other points are measured. The x-axis represents the horizontal position, while the y-axis represents the vertical position. The coordinate of a point is defined as x, y, with x indicating the position along the horizontal axis and y indicating the position along the vertical axis. Pixel coordinates. In computer graphics, pixel coordinates are commonly used to represent the position of a point on a computer screen or image. A pixel represents the smallest unit of display on a screen, and each pixel has a unique position defined by its x and y coordinates. The top left corner of the screen is often considered as the origin, 0, 0, with x increasing towards the right and y increasing towards the bottom. The coordinate 0, 0 represents the top left pixel, while the coordinate width1, height -1 represents the bottom right pixel, where width and height are the dimensions of the screen or image. When working with software libraries for graphics, it is important to understand the coordinate system used by the library. Some libraries may use a different coordinate system than the standard Cartesian or pixel coordinates. It is crucial to consult the documentation or reference materials provided by the library to ensure accurate interpretation and positioning of points. Normalized device coordinates. Normalized device coordinates (NDC) provide a standard coordinate system that is independent of the screen or image resolution. It allows for consistent positioning of objects across different devices. In NDC, the coordinate range is typically from -1 to 1 in both x and y directions. The origin is positioned at the center of the screen or image, with negative x values to the left and positive x values to the right, and negative y values towards the bottom with positive y values towards the top. To convert between pixel coordinates and NDC, scaling and translation operations are often applied. World coordinates. World coordinates are used to represent positions in a user-defined coordinate system that is specific to a particular application or domain. In the context of implementing Delaunay triangulation in 2D graphics, world coordinates can be used to define the positions of points in a plane. These coordinates may relate to real-world distances, such as geographic coordinates or distances in a physical simulation. Converting from world coordinates to screen or pixel coordinates requires a transformation that takes into account the scale, rotation, and translation between the two coordinate systems. Coordinate transformations. Coordinate transformations play a vital role in graphics programming, as they allow for mapping points between different coordinate systems. Transformations can include scaling, rotation, translation, and shearing operations. These operations are commonly applied using matrices in homogeneous coordinate systems. Proper understanding and implementation of these transformations are crucial for correctly rendering graphics and manipulating objects within a coordinate system. Summary. In this section, we have introduced the concept of coordinates and coordinate systems in the context of 2D graphics. We explored the Cartesian coordinate system, which consists of x and y axes, and is commonly used in graphics programming. We also discussed pixel coordinates, which represent positions on a screen or image, and the normalized device coordinates, which provide a standard coordinate system independent of screen or image resolution. Additionally, we touched upon world coordinates, which are used to define a user-specific coordinate system. Finally, we briefly discussed coordinate transformations, which are essential for mapping points between different coordinate systems. Having a solid understanding of coordinates and coordinate systems is crucial for implementing Delaunay triangulation and working with 2D graphics effectively. 2.2 Basic geometric primitives. In 2D graphics, basic geometric primitives are the fundamental building blocks used to create more complex shapes and objects. These primitives include points, lines, polygons, and curves. Understanding and working with these primitives is essential when implementing Delaunay triangulation algorithms in 2D graphics using C. Points. A point is a simple geometric primitive that represents a position in 2D space. In 2D graphics, a point is defined by its x and y coordinates, which determine its position relative to a coordinate system. Each point can be considered as a vertex in a graph, where the connections between vertices form the edges of the graph. When implementing Delaunay triangulation, points are typically used to represent the input data, where each point represents a unique data point on a 2D plane. These points will be the vertices of the resulting triangulation, forming the corners of the triangles. The coordinates of these points are used to calculate the circumcircles and test for the Delaunay property. Lines. Lines are another essential primitive in 2D graphics. In their simplest form, lines consist of 2 points, known as endpoints. These endpoints define the start and end positions of the line. Lines can also be represented by equations, such as slope-intercept form y equals mx plus b, or parametric form x equals x1 plus t, x2 x1, y equals y1 plus t, y2 y1, where t is a parameter that ranges from 0 to 1. In the context of Delaunay triangulation, lines play a crucial role in determining the edges of triangles. Each triangle in the triangulation can be represented by 3 lines, formed by connecting the vertices of the triangle. These lines help us represent the connectivity between the vertices and perform edge-flipping operations to ensure the Delaunay property. Polygons. Polygons are closed geometric shapes formed by connecting multiple line segments. They consist of a set of vertices, with each vertex connected to the next, and the final vertex connected to the first, thus forming a closed shape. Polygons can have any number of sides, and each side is represented by a line segment. In Delaunay triangulation, polygons are not used to represent the final output, as the triangulation aims to decompose the plane into triangles. However, during the construction of the triangulation, polygons play a role in defining the boundary constraints in the convex hull. The convex hull is the smallest convex polygon that contains all input points, and this information is crucial for inserting new points and maintaining the Delaunay property. Curves. Curves in 2D graphics are smooth, continuous lines that are not composed of straight line segments. Curves are defined using mathematical equations or parametric functions, such as Bezier curves or splines. These equations determine the shape and behavior of the curve, allowing for more complex and flexible representations. While curves are not utilized directly in the construction of the Delaunay triangulation, they can be used in specific applications that involve approximating curved boundaries or nonlinear data. By converting curves into a series of points, they can be incorporated into the triangulation process. Summary. Understanding basic geometric primitives is essential when implementing Delaunay triangulation algorithms in 2D graphics. Using C-points represent the input data and form the vertices of the resulting triangulation. Lines are used to define the edges of the triangles and play a crucial role in maintaining the Delaunay property. Polygons define the boundary constraints and the convex hull of the triangulation. Curves, while not directly utilized in the construction of the Delaunay triangulation, can be used to approximate curved boundaries or nonlinear data. By utilizing these basic geometric primitives, we can construct a robust and efficient implementation of the Delaunay triangulation algorithm in 2D graphics using the C programming language. In the next section, we will explore transformation and affine operations, which are essential for manipulating and transforming these geometric primitives. 2.3 Transformation and affine operations. Transformation and affine operations play a crucial role in 2D graphics. They allow us to manipulate and position geometric objects such as points, lines, and triangles on a 2D plane. In the context of implementing Delaunay triangulation, understanding how to apply transformations and affine operations is essential for manipulating the input data and obtaining the desired triangulation. 2.3.1 Translation. Translation is the process of shifting an object's position in the 2D plane. It involves modifying the coordinates of each point by adding or subtracting values from them. In the context of Delaunay triangulation, translation is often used to normalize the input data or to move the points to a specific location. To translate a point x, y by a distance of dx, we can use the following formula. X equals x plus dxy equals y plus di, where x, y, represents the translated point. When implementing Delaunay triangulation, translation can be useful for aligning the points with the coordinate system, centering the points around the origin, or positioning them according to specific requirements. 2.3.2 Scaling. Scaling allows us to modify the size of an object in the 2D plane. It involves multiplying the coordinates of each point by scaling factors in the x and y directions. Scaling factors greater than 1 increase the size of the object, while scaling factors between 0 and 1 shrink it. To scale a point x, y by scaling factors sx, psi, we can use the following formula. X equals xsxy equals y asterisk psi, where x, y, represents the scaled point. In the context of Delaunay triangulation, scaling can be useful for adjusting the spacing between points or for resizing the entire triangulation. 2.3.3 Rotation. Rotation allows us to rotate an object around a specific point in the 2D plane. It involves modifying the coordinates of each point based on a rotation angle and a center of rotation. The rotation angle is usually measured in radians or degrees. To rotate a point x, y around the center of rotation, cx, psi by an angle theta, we can use the following formula. X equals cx plus x, cx cos theta y, psi sin theta y, equals psi plus x, cx sin theta plus y, psi cos theta, where x, y, represents the rotated point. Rotation can be applied in Delaunay triangulation to adjust the orientation of the points or to align them according to specific requirements. 2.3.4 Shearing. Shearing is a transformation that distorts an object in the 2D plane by skewing or slanting it along one axis while leaving the other axis unchanged. This operation is useful for creating non-uniform scaling effects or applying perspective transformations. To shear a point x, y by shearing factors sx, psi, we can use the following formulas. X equals x plus sxy, y equals y plus psi asterisk x, where x, y represents the sheared point. Although shearing might not be commonly used in Delaunay triangulation, it can be beneficial in certain scenarios where non-uniform transformations are required. 2.3.5 Affine transformations. Affine transformations are a combination of translation, scaling, rotation, and shearing operations. They preserve straight lines, parallelism, and proportions between points. Affine transformations can be represented using matrices, where each matrix element corresponds to a specific transformation parameter. In the context of Delaunay triangulation, affine transformations enable us to modify the position, size, and orientation of the input data to achieve the desired triangulation. These transformations can be applied to the points before or after the triangulation process to obtain the desired output. Implementing affine transformations in C involves defining the transformation matrices and applying them to each point individually or in a loop. The resulting transformed points can then be used as input for the Delaunay triangulation algorithm. Understanding and implementing transformation and affine operations is essential for manipulating and positioning the input data in Delaunay triangulation. These operations allow us to translate, scale, rotate, and shear the points to achieve the desired output. By applying these transformations, we can effectively preprocess the input data and generate accurate and visually compelling triangulations. 2.4 Rendering and displaying 2D graphics. Once we have generated the Delaunay triangulation, the next step is to render and display the resulting 2D graphics. Rendering refers to the process of converting the abstract data of the triangulation into visual representations that can be displayed on a computer screen or any other output device. In this section, we will discuss the basic concepts and techniques involved in rendering and displaying 2D graphics. We will explore approaches for visualizing the Delaunay triangulation, including rendering the vertices, edges, and triangles. Additionally, we will cover topics such as color mapping and anti-aliasing to enhance the visual quality of the output. 2.4.1 Visualization of vertices, edges, and triangles. To visualize the Delaunay triangulation, the most basic elements to render are the vertices, edges, and triangles. These elements provide a visual representation of the underlying data and facilitate a better understanding of the triangulation. Rendering vertices. Rendering the vertices is relatively straightforward. Each vertex in the Delaunay triangulation corresponds to a point in the 2D space. We can represent the vertices as small circles or dots on the display screen. To improve clarity, it is common to assign different colors or symbols to distinguish between vertices belonging to the outer hull and interior vertices. Rendering edges. The rendering of edges is crucial as they define the connectivity between vertices and form the boundaries of the triangles in the Delaunay triangulation. One common approach is to render edges as solid lines connecting the corresponding vertices. To enhance visibility, it is beneficial to use a distinctive color or line style for the edges. Rendering triangles. The visual representation of triangles is essential for understanding the structure of the Delaunay triangulation. Each triangle can be rendered as a closed shape with 3 connected edges, forming the boundary of the triangle. Typically, filled polygons are used to represent the triangles, and different colors can be assigned to differentiate between interior and exterior triangles. 2.4.2 Color mapping and visualization techniques. In addition to visualizing the basic elements of the Delaunay triangulation, we can enhance the representation by incorporating color mapping techniques and other visualization techniques. Color mapping. Color mapping is a technique used to assign colors to the vertices, edges, or triangles based on certain properties or attributes. For example, we can use a continuous color gradient to represent a scalar value associated with each vertex, such as elevation or temperature. This allows us to visualize variations in the data across the triangulation. Color mapping can also be applied to edges or triangles based on properties such as length, curvature, or area. Anti-aliasing. Anti-aliasing is a technique used to smooth out jagged edges and reduce visual artifacts caused by the limited resolution of computer screens. It works by blending the colors along the edges to create a smoother appearance. This technique is particularly beneficial when rendering the edges and boundaries of triangles, as it improves the overall visual quality of the triangulation. 2.4.3 Display and interaction. Displaying the rendered triangulation on the screen requires appropriate graphics libraries or frameworks. In the context of C programming language, libraries like OpenGL or SDL, Simple Direct Media Layer, can be used to create a graphical user interface and render the 2D graphics. Creating a window. To display the triangulation, we need to create a window or canvas where the graphics can be rendered. Libraries like OpenGL provide functions to create and manage windows with customizable dimensions and settings. Handling user interaction. Interactivity is another crucial aspect of displaying 2D graphics. Users often need to perform actions such as zooming, panning, or selecting specific elements. Libraries like OpenGL offer event-driven programming models, allowing developers to capture user input events, such as mouse clicks or keyboard strokes, and associate them with specific functionality within the application. This functionality can include features such as zooming in or out, rotating the visualization, or highlighting specific triangles or vertices based on user selections. Animation. In certain applications, it may be necessary to animate the 2D graphics to demonstrate dynamic changes in the Delaunay triangulation or to illustrate a specific process. Animation can help in visualizing the progression of the triangulation algorithm or in conveying the behavior of the data over time. Libraries like OpenGL support various techniques for creating smooth animations, such as frame-by-frame rendering or interpolation between keyframes. Conclusion. Rendering and displaying 2D graphics play a crucial role in visualizing the Delaunay triangulation. By rendering the vertices, edges, and triangles with appropriate visualization techniques and utilizing color mapping and anti-aliasing, we can create visual representations that effectively convey the underlying data. Additionally, incorporating interactivity and animation can further enhance the user experience and understanding of the Delaunay triangulation. 3. Data structures for implementing Delaunay triangulation. 3.1 Point representation. In order to implement Delaunay triangulation in 2D graphics using C, we need to start by defining a suitable data structure to represent the input points. The most straightforward representation for a point in a 2D space is to use a pair of coordinates. In C, we can achieve this by defining a struct to hold the x and y coordinates of a point. Here's an example of how we can define the point struct. Type def struct point. Double x, double y. Point. In this example, each point is represented by a struct with two fields, x and y, which are of type double to accommodate for floating point coordinates. You can choose other appropriate data types based on your specific requirements. With this struct, we can create individual points by assigning values to the x and y fields. For example, point P1 equals 2.0, 3.5. Point P2 equals -1.8, 0.7. In a larger implementation, you would typically store the points in an array to easily manipulate and access them. Here's an example of how we can define and initialize an array of points. Hashtag define max underscore points 100. Point points max underscore points equals 2.0, 3.5 minus 1.8, 0.7, 5.2, minus 2.6. In this example, we've defined an array points of size max underscore points, which allows you to store up to a predetermined maximum number of points. You can adjust max underscore points according to your needs. Once the points are defined and stored, you can use them as input for the Delaunay triangulation algorithm. The algorithm will operate on these point objects and generate a triangulation based on their relative positions. It's worth noting that the point representation discussed here is a basic one and can be extended to include additional information, such as point labels, attributes, or auxiliary data. Depending on your specific application, you may need to modify the point representation accordingly. In addition to the basic point representation, you may also need to consider various operations and functionalities related to points, such as distance calculations, point comparisons, and point transformations. These operations can be implemented as separate functions or integrated within the point struct itself. For example, you can define functions to calculate the Euclidean distance between 2 points, as follows. Hashtag include less than math, h greater than. Double distance point P1, point P2. Double dx equals P2, x, P1, x, double die equals P2, y, P1, y, return sqrt dx dx plus die asterisk die. In this example, the distance function takes 2 points P1 and P2 as input and calculates their Euclidean distance using the Pythagorean theorem. By properly representing and manipulating points, you can lay the foundation for implementing the Delaunay triangulation algorithm in your 2D graphics application. The point representation discussed in this section is a fundamental building block that enables you to work with the input data efficiently and accurately during the triangulation process. 3.2 Triangle representation. In order to efficiently perform Delaunay triangulation in 2D graphics, it is important to have a proper data structure to represent the triangles. The triangle representation plays a crucial role in the algorithm as it allows for quick access to the vertices and edges of each triangle. In this section, we will explore different approaches for representing triangles and discuss their advantages and disadvantages. 3.2.1 Adjacency list representation. One common way to represent triangles in Delaunay triangulation is by using an adjacency list data structure. In this representation, each triangle is represented as a node in the list, and the adjacency information is stored as pointers or indices to neighboring triangles. In the adjacency list representation, each node contains the indices or pointers to its 3 vertices and 3 neighboring triangles. This allows for constant time access to the vertices of a triangle and efficient traversal between neighboring triangles. The adjacency list representation is particularly useful when performing local operations such as edge flips and triangle removals. The main advantage of the adjacency list representation is its simplicity and efficiency in maintaining adjacency information. However, it can be memory intensive, especially when working with large triangulations or when additional attributes need to be associated with each triangle. 3.2.2 Incidence matrix representation. Another approach to triangle representation is by using an incidence matrix. In this representation, each row and column of the matrix represents a triangle, and the entries indicate the incidence relationship between triangles. For example, a non-zero entry at position I, J indicates that triangle I shares an edge with triangle J. The incidence matrix representation provides a compact way to store the connectivity information of triangles. It allows for constant time access to neighboring triangles and is memory efficient, especially when dealing with sparse triangulations. However, updating the incidence matrix can be computationally expensive, especially when inserting or removing triangles from the triangulation. 3.2.3 Half-edge representation. The half-edge data structure is another popular choice for representing triangles in Delaunay triangulation. In this representation, each triangle is represented by 3 half-edges, where a half-edge corresponds to an edge of the triangle. Each half-edge stores pointers or indices to its adjacent half-edge, its origin vertex, and the face or triangle it belongs to. The advantage of the half-edge representation is its compactness and efficiency in representing both triangles and their connectivity. It allows for constant time access to neighboring triangles and edges, and enables efficient traversal of the triangulation. Additionally, the half-edge data structure is well suited for performing local operations such as edge flips and triangle removals. However, the half-edge representation may require additional memory overhead compared to other representations, as each triangle is represented by 3 half-edges instead of a single data structure. Furthermore, updating the half-edge data structure can be complex, especially when performing topological changes to the triangulation. 3.2.4 Hybrid representations. In practice, a combination of different representations is often used to balance memory efficiency and computational efficiency. Hybrid representations leverage the strengths of multiple representations to achieve optimal performance. For example, one common hybrid approach is to use the adjacency list representation for fast connectivity queries, while using the half-edge representation for local topological operations. By combining different triangle representations, it is possible to achieve a good balance between memory usage and computational efficiency. However, implementing and maintaining hybrid representations can be more complex compared to using a single representation. 3.2.5 Choosing the right representation. The choice of triangle representation depends on various factors, including the specific requirements of the application, the size of the triangulation, and the available computational resources. It is important to consider the trade-offs between memory usage and computational efficiency, as well as the complexity of implementation and maintenance. In general, the half-edge representation is a popular choice due to its efficiency in performing topological operations and its compactness. However, if memory usage is a concern or if the triangulation is sparse, the incidence matrix representation or a hybrid representation may be more suitable. The adjacency list representation is also a viable option, particularly for applications that require frequent adjacency queries. Ultimately, the choice of triangle representation should be based on a careful analysis of the specific requirements and constraints of the problem at hand. By selecting an appropriate triangle representation, you can ensure efficient and effective implementation of Delaunay triangulation in 2D graphics using C. 3.3 Edge representation. In the previous sections, we discussed the point and triangle representations used in implementing the Delaunay triangulation algorithm. In this section, we will focus on the edge representation, which plays a crucial role in efficiently storing and manipulating the edges of the triangulation. Edges are the line segments connecting the vertices of the triangles in the Delaunay triangulation. By representing the edges, we can easily traverse the triangulation and perform various operations such as edge flipping and adjusting. There are different ways to represent edges, depending on the requirements of the algorithm and the specific implementation. One common method for the edge representation is to store the information of each edge as a pair of vertex indices. This representation is simple and memory efficient since it only requires storing 2 integer values for each edge. For example, we can define a structure called edge that contains 2 integer variables, v1 and v2 inches, representing the indices of the vertices connected by the edge. Struct edge int v1, int v2. With this representation, we can create an array of edges to store the edges of the triangulation. The number of edges in the array is equal to 3 times the number of triangles, as each triangle has 3 edges. By maintaining an array of edges, we can easily access and manipulate the edges during the execution of the algorithm. Another approach to edge representation is to store additional information along with the vertex indices. One common piece of information to store is the neighboring triangle indices connected to each edge. This information is crucial for performing efficient edge flipping and adjusting operations. To store the neighboring triangles, we can extend the edge structure by adding 2 more integer variables, t1 and t2 inches, representing the indices of the neighboring triangles. If an edge is on the boundary of the triangulation, one of these variables can be set to a flag value, such as -1, to indicate the absence of a neighboring triangle. Struct edge int v1, int v2. Int t1, index of the first neighboring triangle int t2, index of the second neighboring triangle. With this extended representation, we can create an array of edges that not only stores the vertex indices but also tracks the neighboring triangles. This information can greatly improve the efficiency of edge flipping and adjusting operations, as we can easily access the neighboring triangles given an edge. In addition to storing vertex and triangle information, we might also want to store additional data associated with each edge. For example, in certain applications, we may want to assign weights or labels to edges to represent different attributes or properties. In such cases, we can further extend the edge structure to include additional fields for storing the desired information. Struct edge. Int v1, int v2. Int t1, index of the first neighboring triangle. Int t2, index of the second neighboring triangle. Additional fields for storing edge-specific data. By extending the edge representation to include additional data fields, we can easily associate and manipulate various attributes or properties with each edge in the Delaunay triangulation. In conclusion, the edge representation is an important component in implementing the Delaunay triangulation algorithm in 2D graphics using C. The choice of edge representation depends on the specific requirements of the algorithm and the desired functionality. We discussed two common approaches for edge representation: storing just the vertex indices and storing additional information such as the neighboring triangle indices and edge-specific data. By properly representing the edges, we can efficiently store and manipulate the edge information, allowing for the effective construction and manipulation of the Delaunay triangulation. 3.4 Data structures for efficient search and insertion. Efficient search and insertion are key operations in implementing Delaunay triangulation in 2D graphics using C. To achieve optimal performance, it is important to choose appropriate data structures that allow for fast lookup and insertion of points, triangles, and edges. 3.4.1 Point quad tree. One commonly used data structure for efficient point search and insertion is the point quad tree. A quad tree is a recursive data structure that divides space into 4 quadrants. In the context of Delaunay triangulation, each quadrant represents a region of the plane. The root of the quad tree represents the entire plane, and the splitting continues recursively until a predetermined condition is met, e.g., a maximum number of points per leaf or a minimum region size. Each node in the quad tree contains a rectangle that represents its partitioned region. The points are stored in the leaf nodes of the quad tree. When inserting a new point, the quad tree is traversed recursively, starting from the root, until a leaf node is reached. The point is then inserted into the appropriate leaf node. During the search process, the quad tree is traversed recursively based on the region of interest. Only the nodes that intersect with the region of interest are visited, reducing the number of comparisons necessary for point searching. This drastically improves the efficiency of point-based operations in Delaunay triangulation, such as finding the nearest neighbor or locating points within a specified range. 3.4.2 Edge and triangle structures. Efficient search and insertion of edges and triangles can also be achieved through appropriate data structures. One commonly used structure is the half-edge data structure, which represents edges and triangles as interconnected entities. In the half-edge data structure, each triangle is represented by 3 half-edges, with each half-edge pointing to the next half-edge in the triangle. This connectivity allows for efficient traversal and manipulation of the triangulation. Each half-edge also contains references to its start and end vertices, as well as the adjacent triangles. To support fast edge search and insertion, a hash table or a map can be used. The key of the hash table or map is typically a combination of the start and end vertex indices of an edge. This allows for efficient lookup of edges based on their vertices, which is often required during the insertion and removal of edges in the triangulation. Additionally, a priority queue can be used to maintain a sorted list of triangles based on some criteria, such as their circumcircle radius. This allows for efficient access to the triangle with the largest circumcircle radius, which is useful during the flipping and adjusting processes of the Delaunay triangulation algorithm. 3.4.3 Red-black tree. Another data structure that can be utilized for efficient search and insertion is the red-black tree. Red-black trees are self-balancing binary search trees that guarantee O, log n, time complexity for search, insertion, and deletion operations. In the context of Delaunay triangulation, a red-black tree can be used to maintain the sorted list of edges or triangles based on some criteria. This allows for efficient search and insertion of edges or triangles, especially when the number of elements in the structure is large. By utilizing an appropriate comparison function for the elements in the red-black tree, it is possible to maintain a dynamically sorted list of elements while efficiently inserting and searching for specific elements. 3.4.4 Hybrid data structures. In some cases, a combination of data structures may be employed to achieve optimal performance. For example, a hybrid structure may use a point quad tree for efficient point search and insertion, and a red-black tree for maintaining a sorted list of edges or triangles. By combining different data structures and leveraging their individual strengths, it is possible to design more efficient algorithms for Delaunay triangulation. However, it is important to carefully analyze the requirements of the specific application and to choose the appropriate data structures accordingly. In conclusion, efficient search and insertion are crucial for implementing Delaunay triangulation in 2D graphics using C. The choice of data structures, such as point quad trees, half-edge structures, red-black trees, or hybrid combinations, significantly impacts the performance of the algorithms. By carefully selecting and optimizing the data structures, optimal efficiency and speed can be achieved in various operations, ensuring the smooth execution of Delaunay triangulation algorithms in real-world applications. 4. Incremental Delaunay triangulation algorithm. 4.1 Overview of the incremental algorithm. The incremental Delaunay triangulation algorithm is one of the most commonly used algorithms for generating a Delaunay triangulation in 2D graphics. It is known for its simplicity, efficiency, and effectiveness in constructing the triangulation incrementally as new points are added to the existing set. The incremental algorithm starts with an empty triangulation and adds points one by one while maintaining the Delaunay property. The main idea behind this algorithm is to insert each new point into the existing triangulation without violating the Delaunay property, which ensures that the resulting triangulation is well formed and optimal. The algorithm can be summarized in the following steps. Initialization. First, initialize an empty triangulation. This could be done by creating a super triangle that encloses the entire input point set. The super triangle acts as an initial bounding triangle and ensures that no new point lies outside the triangulation. It also simplifies the handling of boundary points. Inserting the first point. Select the first point from the input point set and insert it as the initial vertex of the super triangle. Update the triangulation by connecting the point to the vertices of the super triangle and splitting it into 3 new triangles. Adding subsequent points. For each new point in the input set, locate the triangle in the current triangulation that contains it. This can be done by traversing the triangulation using the point's coordinates. The point will always reside in the triangle whose circumcircle contains the new point. Finding encroached edges. Once the containing triangle is found, check if the new point encroaches any edges of the triangle. An encroached edge is defined as an edge whose circumcircle contains the new point. If any encroached edges are found, they must be flipped to maintain the Delaunay property. Flipping refers to replacing an encroached edge with 2 new edges, connecting the new point to the non-adjacent vertices of the edge. Flipping edges and adding new triangles. Perform the edge flips to remove the encroached edges and create new triangles. After each edge flip, check if any further encroached edges are created. If so, repeat the flipping process until no encroached edges remain. Finally, add the new point to the triangulation by connecting it to the vertices of the last flipped edge and splitting it into new triangles. Repeat step 3 to 5 for all points. Repeat steps 3 to 5 for all the remaining points in the input set. Each new point will be inserted into the existing triangulation, and encroached edges will be flipped as necessary. The Delaunay property will be maintained, and new triangles will be added accordingly. Removing the super triangle. After all the points have been inserted into the triangulation, remove the super triangle to obtain the final Delaunay triangulation. This can be done by removing all triangles that share an edge with the super triangle. The incremental Delaunay triangulation algorithm allows for efficient triangulation construction in an incremental manner. It ensures that the Delaunay property is maintained throughout the process and produces a well-formed triangulation suitable for various applications in 2D graphics. The algorithm is relatively simple to implement in C and provides a practical approach for generating Delaunay triangulations efficiently. 4.2 Initialization and first triangle. In order to start the incremental Delaunay triangulation algorithm, we need to initialize our data structures and create the first triangle. This initial triangle will serve as the seed for inserting the remaining points into the triangulation. Initializing data structures. Before we can begin the triangulation process, we need to set up the necessary data structures to store the points, triangles, and edges. In the previous section, section 3.1-3.4, we discussed different data structures for efficient search, insertion, and representation of the triangulation components. For initializing the data structures, we will start with an empty list of points, an empty list of triangles, and an empty list of edges. As each point is inserted into the triangulation, these data structures will be updated accordingly to maintain the consistency of the triangulation. Creating the first triangle. The first triangle is crucial to kickstart the incremental Delaunay triangulation algorithm. We need to carefully choose the points for the vertices of this triangle to ensure a good foundation for the subsequent insertions. There are various ways to choose the initial triangle, but an approach that guarantees a robust triangulation is to create an auxiliary super triangle that fully contains the input point set. This super triangle should be large enough to enclose the entire domain of the input points. To create the super triangle, we can take the minimum and maximum coordinates of all the points and then extend the triangle's sides to make it larger. The vertices of the super triangle should be well outside the domain of the input points to avoid any interference during the insertion process. Once the super triangle has been defined, we add it to our list of triangles and update our data structures accordingly. The super triangle will serve as the reference triangle for the subsequent insertions. Inserting the points. With the initialization and the creation of the first triangle complete, we can now proceed to insert the remaining points into the triangulation. The incremental algorithm works by adding one point at a time to the existing triangulation. For each point to be inserted, we perform a series of steps. Search. We search for the triangle that contains the new point. This search is done efficiently by starting from the current triangle of the previous insertion and traversing the triangulation by following the edges until we find the enclosing triangle. This search can be performed using techniques like point location algorithms or spatial data structures. Split. Once we locate the enclosing triangle, we split it into 3 new triangles by connecting the new point with each of the triangle's vertices. We update our data structures to incorporate these new triangles and edges. Adjust. After splitting the enclosing triangle, we need to adjust the connectivity of the triangulation to maintain the Delaunay property. This adjustment involves checking for the need to flip edges and optimizing the triangle's orientations. By performing the necessary edge flips and orientations adjustments, we ensure that the inserted point respects the Delaunay property. Repeat. We repeat the search, split, and adjust steps for all the remaining points until the entire set of points has been inserted. By following this process iteratively, we gradually build the Delaunay triangulation of the input point set. Conclusion. The initialization and creation of the first triangle are essential steps in implementing the incremental Delaunay triangulation algorithm. By properly setting up the data structures and choosing a suitable initial triangle, we establish the foundation for inserting the remaining points and creating a robust Delaunay triangulation. In the next section, we will delve into the details of adding points to the triangulation and explore the processes of splitting triangles and adjusting the triangulation to maintain the Delaunay property. 4.3 Adding points to the triangulation. In the incremental Delaunay triangulation algorithm, points are added one by one to the existing triangulation. This section will explain the process of adding points to the triangulation and maintaining the Delaunay property. When starting with an empty triangulation, the first 3 points are used to create an initial triangle. To add a new point P to the triangulation, the algorithm first finds the containing triangle for the point. This can be done by performing a localized search starting from an arbitrary triangle in the triangulation. Once the containing triangle is found, the algorithm will insert the new point into the triangulation. The localized search starts at a triangle and traverses through the triangulation by always moving to the neighbor triangle that contains the point being searched. This process is done iteratively until the containing triangle for the new point is found. To perform the localized search efficiently, a search data structure such as a quad tree or an AABB tree can be utilized. Once the containing triangle is identified, the algorithm creates 3 new triangles by connecting the new point to each vertex of the containing triangle. The edges of the new triangles are then checked to ensure they do not intersect with any other triangles in the triangulation. If an intersection is detected, it indicates that the new point lies inside one of the existing triangles. In this case, the algorithm will perform a series of edge flips and adjustments to restore the Delaunay property. Edge flipping involves replacing an old edge with a new edge by connecting the non-shared vertices of 2 neighboring triangles. This process adjusts the connectivity of the triangulation while maintaining the Delaunay property. The edge flipping process continues until all new triangles no longer have intersecting edges with any other triangles in the triangulation. In some cases, additional points may need to be added during the edge flipping process. These new points are inserted in the same way described above, using a localized search to find the containing triangle and then connecting the point to each vertex of the containing triangle. The addition of points in the corresponding edge flipping process continues until all points have been added to the triangulation. At the end of the algorithm, the resulting triangulation is a Delaunay triangulation of the input points. The Delaunay property ensures that no point lies inside the circumcircle of any triangle in the triangulation. It is important to note that the order in which points are added to the triangulation can affect the efficiency and stability of the algorithm. Certain point orderings can lead to a high number of edge flipping operations, which can degrade the performance of the algorithm. To mitigate this issue, techniques such as random shuffling or spatial sorting of the points can be employed to achieve better triangulation results. The process of adding points to the triangulation can be implemented efficiently using appropriate data structures. For example, a half-edge data structure can be used to represent the connectivity between triangles, allowing for efficient traversal and modification of the triangulation. Additionally, using a spatial data structure like a quad tree can aid in the localized search process, improving the overall performance of the algorithm. In summary, the process of adding points to the Delaunay triangulation involves finding the containing triangle for each new point through a localized search, connecting the new point to each vertex of the containing triangle to create new triangles, and performing edge flipping and adjustments to maintain the Delaunay property. Efficient data structures and point ordering strategies can greatly impact the performance and stability of the algorithm. 4.4 Flipping and adjusting the triangulation. In the previous section, we discussed the process of adding points to the triangulation through the incremental Delaunay triangulation algorithm. However, as we continue adding points to the existing triangulation, it is important to maintain the Delaunay property. In this section, we will explore the concept of flipping and adjusting the triangulation to ensure that the Delaunay property is preserved. 4.4.1 Flipping. As new points are inserted into the triangulation, it is possible that the Delaunay property may be violated, specifically the Delaunay condition which states that no point should lie within the circumcircle of any triangle in the triangulation. In order to fix this violation, we can perform a flipping operation. A flip operation involves replacing an existing edge in the triangulation with a new edge, hence changing the connectivity between triangles. The goal is to ensure that the Delaunay property is restored. The process can be summarized as follows. Identify the edge that violates the Delaunay condition. Let's call this edge AB. Find the opposite vertex to AB, which is the vertex not shared by the triangles on either side of AB. Let's call this vertex C. Remove the triangles ABC and ACD from the triangulation. Create new triangles BCD and OBID by connecting the appropriate vertices. Repeat this process for all the edges that violate the Delaunay condition. It is worth noting that the order in which the flips are performed can influence the final triangulation. Different orderings can lead to different triangulations while still preserving the Delaunay property. 4.4.2 Adjusting the triangulation. In addition to flipping, it may also be necessary to adjust the location of existing vertices in the triangulation as new points are added. This is done to accommodate the newly inserted points and maintain the Delaunay property. Adjusting the triangulation involves updating the coordinates of the existing vertices to improve the Delaunay quality. This can be achieved through a process known as edge swapping. The idea is to swap edges in the triangulation to obtain better quality triangles. The edge swapping process can be summarized as follows. Identify a triangle in the triangulation. Compute the quality metric of the triangle, which can be based on angles, edge lengths, or other factors. If the quality metric is below a certain threshold, consider swapping the edge opposite the longest edge of the triangle. Perform the edge swap by replacing the existing triangle with two new triangles, formed by connecting the appropriate vertices. Repeat this process for all triangles in the triangulation. The goal of adjusting the triangulation is to improve the overall quality of the triangles, which can impact the accuracy of subsequent calculations or visualizations based on the triangulation. 4.4.3 Trade-offs and considerations. While flipping and adjusting techniques are effective in maintaining or improving the Delaunay property of a triangulation, they also come with certain trade-offs and considerations. One consideration is the computational cost of performing flips and adjustments. The process can be expensive, especially as the size of the triangulation increases. Therefore, it is important to optimize the algorithms to ensure efficiency, such as using spatial data structures and parallelization techniques. Another consideration is the potential impact on the characteristics of the triangulation. Flipping and adjusting may alter the connectivity and layout of the triangulation, which can have implications for subsequent operations relying on the triangulation. For example, in certain cases, flipping may introduce short, skinny triangles that can adversely affect the results of surface interpolations or other calculations. It is also worth mentioning that flipping and adjusting may not always be necessary or beneficial. In some cases, the initial triangulation may already satisfy the Delaunay property, or the quality of the triangles may not significantly impact the intended use of the triangulation. Therefore, it is important to assess the specific requirements and constraints of the application when deciding whether to apply flipping and adjusting operations. Overall, flipping and adjusting are important techniques in maintaining or improving the Delaunay property of a triangulation in 2D graphics. By performing these operations, we can ensure that the Delaunay triangulation accurately represents the underlying geometry and facilitates various applications such as interpolation, mesh generation, and spatial analysis. 5. Delaunay triangulation algorithms. 5.1 Bowyer-Watson algorithm. The Bowyer-Watson algorithm is one of the most well-known and widely used algorithms for computing the Delaunay triangulation in two-dimensional space. It is an incremental algorithm that starts with an empty triangulation and adds points one by one, maintaining the Delaunay property throughout the process. The process begins by defining a large triangle that encloses the entire set of points, ensuring that no point lies outside this bounding triangle. This triangle acts as an initial seed for the triangulation. To add a new point to the triangulation, the algorithm identifies the triangle in which the point lies, forming a cavity. It then removes this cavity by flipping the affected edges and creating new triangles. The algorithm continues this process for all the points, incrementally updating the triangulation until every point has been added. The main steps of the Bowyer-Watson algorithm are as follows. Initialize the triangulation. Create a large bounding triangle that encloses all the points. This triangle should be large enough to cover the entire plane. This can be achieved by finding the minimum and maximum x and y coordinates of the input points. Iterate over each point. For each point in the input set, find the triangle in which the point lies. This can be done by starting with the bounding triangle and recursively moving from triangles to adjacent triangles until the point is found. Remove the cavity. Once the triangle containing the point is found, remove it along with all the triangles sharing an edge with it, creating a cavity in the triangulation. Flip edges and create new triangles. For each edge of the cavity, check if it is a Delaunay edge. An edge is Delaunay if its opposite vertex lies inside the circumcircle of the triangle formed by the edge and the newly added point. If an edge is not Delaunay, flip it and create two new triangles. Repeat this process for all edges of the cavity. Repeat steps 2 to 4 for all points. Continue adding points one by one and updating the triangulation until every point has been processed. At the end of the Bowyer-Watson algorithm, the resulting triangulation will satisfy the Delaunay property, which states that for all triangles in the triangulation, no point lies inside the circumcircle of any triangle. The Bowyer-Watson algorithm is relatively straightforward to implement and has a worst-case runtime complexity of O(n squared, where n is the number of input points. However, in practice, it often has a much better performance and can handle large datasets efficiently. One of the advantages of the Bowyer-Watson algorithm is its simplicity and ease of understanding. It provides a clear and intuitive approach to constructing the Delaunay triangulation. Additionally, the algorithm maintains the Delaunay property throughout the triangulation process, ensuring the quality and validity of the resulting triangulation. However, the Bowyer-Watson algorithm has some limitations. It is not well suited for dynamic or real-time scenarios where points are constantly being added or removed, as the algorithm would need to be repeated from scratch each time. It also requires significant memory overhead to store the triangulation data structures. Overall, the Bowyer-Watson algorithm is a fundamental and widely used algorithm for computing the Delaunay triangulation in 2D graphics. It provides an efficient and effective method for generating a triangulation that satisfies the Delaunay property. 5.2 Sweep Line Algorithm. The sweep line algorithm is another popular method for implementing Delaunay triangulation in 2D graphics. Unlike the Bowyer-Watson algorithm that we discussed in the previous section, the sweep line algorithm works by sweeping a line across the points in the plane, processing them one by one. This algorithm is also known as the vertical decomposition method and is based on the concept of line sweeping. Overview of the sweep line algorithm. The sweep line algorithm starts by sorting the input points based on their x-coordinates in ascending order. This sorted list of points is then traversed from left to right, with a line sweeping across the points at each step. As the line sweeps through the points, it maintains a dynamic data structure, typically a balanced binary search tree (BST) that keeps track of the current triangulation. At each point, the algorithm updates the triangulation by inserting the current point into the existing triangulation and adjusting the edges and triangles as necessary to maintain Delaunay properties. This is done by checking the neighboring points of the current point that are already inserted into the triangulation and performing edge flips if necessary to satisfy the Delaunay condition. To efficiently identify the neighboring points, the algorithm uses a technique called sweepline status. The sweepline status maintains a vertical ordering of the inserted points, which allows for efficient neighbor lookup. By storing the points in the BST, the algorithm can quickly find the points below and above the current point in terms of their y-coordinates. Implementation steps. The implementation of the sweepline algorithm involves the following steps. Sort the input points based on their x-coordinates in ascending order. Initialize an empty BST to store the points inserted into the triangulation. Start sweeping the line from left to right. For each point, insert it into the BST and update the triangulation by checking neighboring points and performing edge flips as necessary. Update the sweepline status after each insertion to maintain the vertical ordering of points. Continue sweeping until all points have been processed. Finally, output the resulting triangulation. Advantages of the sweep line algorithm. The sweep line algorithm offers several advantages compared to other Delaunay triangulation algorithms. Efficient time complexity. The sweep line algorithm has a time complexity of O(n log n), where n is the number of input points. This makes it one of the fastest algorithms for Delaunay triangulation. Simplicity of implementation. The algorithm is relatively straightforward to implement, requiring basic data structures like a BST and simple geometric operations like point insertion and edge flipping. Incremental construction. The sweepline algorithm lends itself well to incremental construction, allowing for efficient updates when new points are added or existing points are removed from the triangulation. Deterministic output. The algorithm produces a unique triangulation regardless of the order in which the input points are processed. Limitations of the sweepline algorithm. While the sweepline algorithm has many advantages, it also has some limitations to consider. Restriction to 2D. The sweepline algorithm is specifically designed for 2D triangulation and cannot be easily extended to higher dimensional spaces. Boundary constraints. The algorithm may require additional steps to handle boundary points or constraints, such as incorporating the convex hull into the triangulation or enforcing specific edge connections. Memory usage. The algorithm may require additional memory to store the BST and other data structures used in the sweepline status, which can impact performance and memory usage for large datasets. Sensitivity to degenerate cases. Like other Delaunay triangulation algorithms, the sweepline algorithm may encounter degenerate cases, such as collinear or coincident points, which can affect the robustness and reliability of the algorithm. Summary. The sweepline algorithm is a fast and efficient method for implementing Delaunay triangulation in 2D graphics. By sweeping a line across the input points and maintaining a dynamic triangulation, the algorithm can construct the Delaunay triangulation in a deterministic and incremental manner. Although it has some limitations, the sweepline algorithm remains a popular choice for applications where speed and simplicity are essential. 5.3 Divide and Conquer Algorithm. The divide and conquer algorithm is another popular method for implementing Delaunay triangulation in 2D graphics. This algorithm breaks down the problem into smaller subproblems, solves them independently, and then combines the solutions to form the final triangulation. Algorithm overview. The divide and conquer algorithm for Delaunay triangulation can be summarized in the following steps. Divide the set of points into two equal-sized subsets. Recursively compute the Delaunay triangulation for each subset. Merge the two triangulations by finding the lower common tangent and connecting the corresponding convex hulls. Check for any new edges that need to be added by removing illegal edges. Repeat steps 3 and 4 until a single triangulation is obtained. Advantages and limitations. The divide and conquer algorithm offers several advantages over other Delaunay triangulation algorithms. Efficiency. The algorithm has a time complexity of O n log n, which is the best achievable time complexity for solving the Delaunay triangulation problem in the plane. Parallelization. The divide and conquer approach lends itself well to parallelization, allowing for faster computation of the triangulation on multi-core or distributed systems. Ease of implementation. The algorithm can be implemented using simple recursive procedures, making it relatively straightforward to understand and implement. However, the divide and conquer algorithm also has some limitations. Memory usage. The algorithm requires additional memory to store the intermediate triangulations during the merging process, potentially leading to increased memory usage for larger input datasets. Edge cases. The algorithm may struggle with certain edge cases, such as degenerate or highly clustered point configurations, which can result in suboptimal triangulations or increased computational complexity. Algorithm implementation. To implement the divide and conquer algorithm for Delaunay triangulation in 2D graphics using C, you can follow these steps. Sort the input points in increasing order of their x-coordinates. Divide the sorted points into two equal-sized subsets based on their x-coordinate. Recursively compute the Delaunay triangulation for each subset. Merge the two triangulations by finding the lower common tangent, connecting the corresponding convex hulls, and removing any illegal edges. Repeat steps 3 and 4 until a single triangulation is obtained. Here is a pseudocode representation of the divide and conquer algorithm. Recursive function to compute Delaunay triangulation void divide and conquer points, int left, int right. If right, left equals 1. Base case, 2 points, create a single edge connect points right. Else if right, left greater than 1. Int mid equals left plus right 2. Recursive calls divide and conquer points, left, mid divide and conquer points, mid plus 1, right. Merge the triangulations merge triangulations points, left, mid, right. Function to merge two triangulations void merge triangulations points, int left, int mid, int right. Find the lower common tangent point LC tangent equals find lower common tangent points, left, mid, right. Connect the corresponding convex hulls connect convex hulls points, left, mid, LC tangent connect convex hulls points, mid plus 1, right, LC tangent. Remove any illegal edges remove illegal edges points, left, mid, right. Main function to compute Delaunay triangulation void Delaunay triangulation points, int n. Sort points in increasing order of x-coordinate sort points n. Call the divide and conquer algorithm divide and conquer points, 0, n1. You can implement the necessary helper functions such as connect, find lower common tangent, connect convex hulls, remove illegal edges, and sort points based on your specific programming needs and environment. Summary. The divide and conquer algorithm for Delaunay triangulation offers an efficient and parallelizable approach to computing the triangulation of a set of points in 2D graphics. By dividing the problem into smaller subproblems and merging the solutions, this algorithm provides a robust solution for various applications that require Delaunay triangulation. However, it is important to consider the algorithm's limitations, such as increased memory usage and potential issues with edge cases. 5.4 Comparison of different algorithms. In this section, we will compare and evaluate different algorithms for implementing Delaunay triangulation in 2D graphics using the C programming language. Each algorithm has its own strengths and weaknesses in terms of performance, efficiency, and computational complexity. By understanding the trade-offs associated with each algorithm, developers can make informed decisions when choosing the most suitable approach for their specific application. 5.4.1 Bowyer-Watson algorithm. The Bowyer-Watson algorithm is one of the most well-known and widely used algorithms for Delaunay triangulation. It is based on incremental insertion, where triangles are added to the triangulation one at a time. The algorithm starts with a super triangle that encompasses all the points and iteratively inserts each point into the triangulation. One advantage of the Bowyer-Watson algorithm is its simplicity and ease of implementation. It is relatively straightforward to understand and code, making it a popular choice for beginners. However, it can suffer from performance issues when dealing with large datasets. The computational complexity of the algorithm is O(n squared, where n is the number of input points, which limits its scalability for massive datasets. 5.4.2 Sweep line algorithm. The sweep line algorithm is another commonly used approach for Delaunay triangulation. It utilizes a line sweeping technique to iteratively process the points in a horizontal or vertical order and construct the Delaunay triangulation incrementally. The concept of tangents and line segments plays a crucial role in the algorithm. One significant advantage of the sweep line algorithm is its efficiency in terms of time complexity. It achieves a time complexity of O(n log n, making it suitable for handling large datasets. This attribute makes it a preferred choice for real-time applications such as computer graphics, where fast triangulation is required. However, implementing the sweep line algorithm can be more complex compared to the Bowyer-Watson algorithm due to the involved geometric computations. 5.4.3 Divide and conquer algorithm. The divide and conquer algorithm is another popular approach for Delaunay triangulation. It follows a divide and conquer strategy where the plane is recursively divided into smaller subproblems until the triangulation can be easily solved. This algorithm partitions the input points into two subsets and computes the Delaunay triangulation for each subset separately. Finally, it merges the two triangulations into a single triangulation. One advantage of the divide and conquer algorithm is its efficient time complexity of O(n) log n. It also fares better than the Bowyer-Watson algorithm in terms of scalability as it can handle larger datasets. However, the divide and conquer algorithm may suffer from increased memory consumption due to the recursive nature of the algorithm. It also requires additional computation to merge the separate triangulations, adding complexity to the implementation. 5.4.4 Comparison and Selection. When choosing the appropriate algorithm for implementing Delaunay triangulation in 2D graphics using C, it is essential to consider the specific requirements of the application. Here are some considerations to weigh. Input data size. If the input dataset is small or moderate in size, the Bowyer-Watson algorithm can be a suitable choice due to its simplicity. However, if the dataset is large, the sweep-line or divide and conquer algorithms might be more suitable due to their better time complexity. Performance requirements. For real-time applications that demand quick triangulation, such as interactive graphics, the sweep-line algorithm is generally a good choice due to its efficient time complexity. Implementation complexity. The Bowyer-Watson algorithm is generally simpler to implement compared to the sweep-line and divide and conquer algorithms, making it a good choice for beginners or projects with limited resources and tight deadlines. Memory constraints. If the available memory is limited, the Bowyer-Watson algorithm might be a better choice as it requires less memory compared to the divide and conquer algorithm, which incurs additional costs for merging triangulations. Spatial distribution of points. Depending on the spatial distribution of the input points, certain algorithms may perform better. It is recommended to test different algorithms on sample datasets representative of the actual data to determine the most suitable option. In practice, it is advisable to benchmark and profile different algorithms using representative datasets and performance metrics to understand their behavior and select the most appropriate solution for the specific application. Overall, all three algorithms discussed have their strengths and weaknesses, and the choice of algorithm depends on the specific requirements of the application. By considering factors such as dataset size, performance requirements, implementation complexity, memory constraints, and spatial distribution of points, developers can make informed decisions when selecting the most appropriate algorithm for implementing Delaunay triangulation in 2D graphics using C. 6. Checking the Delaunay property. 6.1 Definition of the Delaunay property. In the previous chapters, we have discussed various algorithms and data structures used in implementing Delaunay triangulation. In this section, we will dive deeper into the concept of the Delaunay property and understand what it means for a triangulation to be Delaunay. The Delaunay property is a fundamental property of Delaunay triangulations. It can be defined as follows. Given a set of points in the plane, a triangulation of those points is said to satisfy the Delaunay property if and only if the circumcircle of every triangle in the triangulation contains no other point from the set in its interior. To understand this definition, let's break it down. Circumcircle. The circumcircle of a triangle is the unique circle that passes through all three vertices of the triangle. It is important to note that the circumcircle of a degenerate triangle, where the 3 points are collinear, is simply a straight line. Interior of a circle. The interior of a circle consists of all points that are strictly inside the circle, excluding the points on the circumference. Based on these definitions, we can state that a triangulation satisfies the Delaunay property if and only if no point lies inside the circumcircle of any triangle in the triangulation. The Delaunay property is essential because it ensures geometric optimality in the triangulation. Triangulations that satisfy the Delaunay property have several desirable properties. Empty circumcircles. In Delaunay triangulations, there are no points inside the circumcircles of triangles. This property helps to minimize the overlapping of triangles and ensures a more uniform distribution of triangles in the plane. Minimum angle condition. The Delaunay property ensures that the minimum angle in a triangle is maximized. This guarantees a more robust and well-shaped mesh, as triangles with larger angles tend to be more suitable for various applications like finite element analysis and computational geometry. Longest edge property. Delaunay triangulations maximize the length of the smallest edge among adjacent triangles. Large minimum edge lengths are valuable in applications such as finite element simulation, where smaller edges can introduce error or instability. One approach to checking if a given triangle satisfies the Delaunay property is to compute the circumcircle of the triangle and then check if any other points lie inside it. This process involves utilizing the concept of the determinant and computing the signed area of triangles. Given a triangle with vertices A, B, and C, a point P lies inside the circumcircle of the triangle if and only if the determinant of the matrix Ax, Pxi, Py Ax, Px squared plus I, Py squared Bx, Px by, Py Bx, Px squared plus by, Py squared Cx, Px psi, Py Cx, Px squared plus psi, Py squared is positive. With this information, we can design algorithms to check the Delaunay property and ensure that our triangulations meet this critical criterion. The ability to efficiently determine if a triangulation is Delaunay is crucial in maintaining correctness and optimizing performance in various applications. In the next section, we will explore the process of determining the circumcircle of a triangle, which is a key step in verifying the Delaunay property. By understanding the definition of the Delaunay property and how it is checked, we can appreciate the significance of this criterion in the context of Delaunay triangulation. This understanding will help us design efficient algorithms and data structures to ensure the correctness and effectiveness of our implementations. 6.2 Determining the circumcircle of a triangle. In the context of Delaunay triangulation, one crucial step is checking whether a given triangle satisfies the Delaunay property. This property states that for any three vertices of a triangle in a Delaunay triangulation, the circumcircle of the triangle should not contain any other points from the dataset. To determine whether a point lies inside or outside the circumcircle of a triangle, we need to find the center and radius of the circumcircle. The circumcircle of a triangle is a circle that passes through all three vertices of the triangle. Once we have the circumcircle, we can compare the distance between the circumcenter and the point of interest with the radius of the circumcircle to determine its location. Calculating the circumcircle. To find the circumcircle of a triangle, we can use the following steps. Identify the three vertices of the triangle, denoted as A, B, and C. Calculate the midpoints of two edges of the triangle, which can be obtained by finding the averages of the coordinates of the two vertices forming each edge. Denote these midpoints as M1 and M2. Find the slopes of the edges, also known as the perpendicular bisectors. The slopes of the perpendicular bisectors can be determined by taking the negative inverses of the slopes of the corresponding triangle edges. Using the slopes and the midpoints, calculate the equations for the bisector lines, y equals mx plus b, where m represents the slope and b represents the y-intercept of each bisector. Find the intersection point of the two bisector lines, which gives the center of the circumcircle. This can be achieved by solving the system of equations formed by the equations of the bisectors. Calculate the distance between the center of the circumcircle and any of the triangle vertices to obtain the radius of the circumcircle. Determining point position. Once we have the circumcircle, we can determine the position of a point P relative to a triangle ABC by comparing the distance between P and the circumcenter with the radius of the circumcircle. Calculate the distance d between the circumcenter and the point P using the distance formula, d equals sqrt_px, cx squared plus py, psi squared, where px and py represent the coordinates of point P, and cx and psi represent the coordinates of the circumcenter. Compare d with the radius of the circumcircle. If d is less than the radius, then the point P lies inside the circumcircle. If d is greater than the radius, the point P lies outside. Floating point precision issues. One common challenge when implementing the circumcircle calculation is dealing with floating point precision issues. Due to the nature of floating point arithmetic, there can be rounding errors and inconsistencies that may affect the accuracy of the circumcircle calculation. These errors can lead to incorrect determinations of the Delaunay property. To mitigate these precision problems, it is essential to use appropriate algorithms and data types that provide sufficient precision for the calculations. Care should also be taken to handle degenerate cases such as collinear points or triangles with zero or very small areas. These cases can introduce numerical instability and should be treated separately to ensure accurate results. Performance considerations. Calculating the circumcircle of a triangle involves several mathematical operations, such as solving systems of equations and computing square roots. These operations can be computationally expensive, especially when performed for a large number of triangles in a Delaunay triangulation. To optimize the performance of determining circumcircles, consider the following techniques. Precompute and cache circumcircles whenever possible, especially in cases where the triangulation does not change frequently. This approach can significantly reduce the computational overhead by avoiding redundant calculations. Utilize appropriate data structures, such as quad-edge or half-edge data structures, to efficiently store and retrieve the triangle and circumcircle information during the triangulation process. Implement algorithms with complexity optimizations, such as using fast square root approximations or avoiding unnecessary calculations when certain conditions are met. Consider parallelization or multi-threading techniques to distribute the computational load across multiple processors or threads, especially for large-scale triangulations. By carefully considering the computational complexity and employing suitable optimization techniques, it is possible to achieve efficient and accurate determinations of circumcircles, thereby ensuring the correct implementation of the Delaunay triangulation algorithm. 6.3 Checking if a triangulation is Delaunay. After understanding the Delaunay property and how to determine the circumcircle of a triangle, it is essential to know how to check whether a given triangulation satisfies the Delaunay condition. In this section, we will discuss the algorithm to check if a triangulation is Delaunay. This algorithm can be used to validate the results obtained from Delaunay triangulation algorithms and ensure the correctness of the triangulation. To check if a triangulation is Delaunay, the algorithm iterates through all triangles in the triangulation and tests each triangle for the Delaunay property. The algorithm follows these steps. Iterate through each triangle in the triangulation. For each triangle, obtain the three vertices of the triangle and calculate the circumcenter and circumradius of the triangle using the methods discussed in section 6.2. Check if any of the neighboring triangles share an edge with the current triangle. For each neighboring triangle, calculate its circumcenter and circumradius. If the circumcircle of a neighboring triangle lies within the circumcircle of the current triangle, then the triangulation violates the Delaunay property. If any violation is found, mark the triangulation as non-Delaunay. Continue this process for all triangles in the triangulation. If no violations are found after checking all triangles, the triangulation satisfies the Delaunay property. By iterating through each triangle in the triangulation and checking its neighboring triangles, we can ensure that the Delaunay property is satisfied. This algorithm has a time complexity of n squared, where n is the number of triangles in the triangulation. However, this algorithm can be further optimized by using efficient data structures discussed in Chapter 3. It is important to note that the algorithm assumes a well-formed triangulation as its input. If the triangulation is malformed or contains degenerate cases, additional error handling may be required. Handling such cases is discussed in Section 7.4. In practical implementations, the correctness of the Delaunay triangulation algorithm is of utmost importance. Therefore, it is recommended to perform thorough testing and validation to ensure the triangulation satisfies the Delaunay property. This involves generating test cases with known results and comparing the output of the algorithm to the expected results. To validate the implementation, it is also useful to compare the results obtained from different Delaunay triangulation algorithms discussed in Chapter 5. This can aid in identifying any discrepancies or potential implementation errors. Additionally, visual inspection of the triangulation can provide a quick way to detect any violations of the Delaunay property. In conclusion, checking if a triangulation is Delaunay involves iterating through each triangle, calculating the circumcircle, and comparing it to the circumcircles of neighboring triangles. This process ensures the Delaunay property is satisfied. Thorough testing and validation are essential to guarantee the correctness of the implementation, and comparing the results from different algorithms can help identify any potential errors. 7. Delaunay triangulation in practice. 7.1 Input data preparation. Before performing Delaunay triangulation in 2D graphics using C, it is important to properly prepare the input data. The quality and organization of the input data can significantly impact the efficiency and accuracy of the triangulation process. This section will discuss the key considerations and techniques for preparing input data for Delaunay triangulation. 7.1.1 Data format. The first step in preparing the input data is to determine the appropriate format for representing the points that require triangulation. The most common format is a list of 2D Cartesian coordinates. Each point in the list represents a vertex of the triangulation. In C, you can represent a point using a struct or a class that contains two variables representing the x and y coordinates. Alternatively, you can use a simple array or a tuple to store the coordinates. The choice of data structure depends on your programming style and requirements. 7.1.2 Point generation. In some cases, the input data for triangulation may be given as a set of discrete points. However, in many graphics applications, the points need to be generated based on a specific pattern or distribution. Some common methods for generating points include random point generation. This method involves generating points randomly within a given region. The random distribution can be uniform or follow a specific probability distribution, such as Gaussian or Poisson. Grid point generation. A grid-based approach generates points in a regular pattern, such as a square or rectangular grid. The grid can be uniform or have varying spacing between points. Voronoi diagram point generation. Voronoi-based methods generate points based on the Voronoi diagram of a set of existing points. Each generated point corresponds to the centroid of a Voronoi cell, resulting in a more evenly distributed set of points. The choice of point generation method depends on the specific requirements of your application. For example, random point generation may be suitable for simulating natural phenomena, while grid-based generation may be appropriate for structured graphics or scientific visualization. 7.1.3 Data validation. Before proceeding with the triangulation process, it is essential to validate the input data to ensure its correctness and reliability. Some common validation steps include bounds checking. Ensure that the input data falls within the desired spatial bounds or region of interest. Points lying outside the bounds can be ignored, discarded, or clipped. Duplicate point removal. Eliminate any duplicate points from the input data, as having duplicate points can result in incorrect or degenerate triangulations. Collinear point removal. Remove any collinear points from the input data. Collinear points do not contribute to the triangulation and can cause potential issues during the process. Outlier detection. Identify and handle outliers, which are points significantly distant from the main dataset. Outliers can disrupt the triangulation and adversely affect the accuracy of the results. Data validation is crucial, as any errors or inconsistencies in the input data can lead to incorrect triangulations or even program crashes. By ensuring the input data's validity, you can minimize the risk of such issues arising. 7.1.4 Preprocessing. Depending on the specific requirements of your application, you may need to perform additional preprocessing steps on the input data before triangulation. Some common preprocessing techniques include normalization. Normalize the input data to a standard range or scale to improve consistency and avoid issues such as numerical instability or precision errors. Sorting. Sort the input points based on a specific criterion such as their x-coordinate or y-coordinate. Sorting can facilitate efficient search and insertion operations during the triangulation process. Delaunay constraints. If your application requires specific Delaunay constraints, such as edges or regions that must be included or avoided, you can preprocess the input data to enforce these constraints. This typically involves introducing additional points or modifying the existing points. 7.1.5 Data Input Methods. Once the input data is prepared, you need to devise suitable methods for providing the data to the Delaunay triangulation algorithm. There are various ways to input the data, depending on the complexity of your application. Direct input. In simple cases, you can directly specify the input data within the code itself. The code can include an array or a list of points, which are then used for triangulation. File input-output. For more complex scenarios, it may be preferable to read the input data from files. This allows you to store and retrieve large datasets conveniently. You can define a specific file format to represent the points or use existing standard formats such as CSV, JSON, or XML. User input. In interactive graphics applications, you can provide mechanisms for users to input or manipulate the data in real time. This allows users to dynamically modify the triangulation based on their requirements. The choice of input method depends on the nature of your application and its specific needs. Consider factors such as data size, usability, and flexibility. By following the techniques discussed in this section, you can effectively prepare the input data for Delaunay triangulation in 2D graphics using paying attention to data format, point generation, validation, preprocessing, and input methods will ensure accurate and efficient triangulation results. 7.2 Choosing the right algorithm. Choosing the right algorithm for Delaunay triangulation is crucial as it can greatly impact the performance and accuracy of the triangulation process. In this section, we will discuss the different algorithms available for Delaunay triangulation in 2D graphics and provide guidelines for selecting the most appropriate one for your specific needs. 7.2.1 Bowyer-Watson algorithm. The Bowyer-Watson algorithm is one of the most widely used algorithms for Delaunay triangulation. It is an incremental algorithm that starts with an empty triangulation and iteratively adds points to the triangulation. The basic idea behind the Bowyer-Watson algorithm is to divide the plane into a set of triangles and iteratively add each point to the triangulation by inserting it into the existing triangles. After inserting a point, the algorithm checks for the Delaunay property and performs edge flipping to maintain the property if necessary. The Bowyer-Watson algorithm is relatively simple to implement and has a time complexity of n squared, where n is the number of input points. However, it can suffer from numerical instability when dealing with degenerate or nearly collinear points. In such cases, the algorithm may produce incorrect results or fail to terminate. 7.2.2 Sweep line algorithm. The sweep line algorithm is another popular algorithm for Delaunay triangulation. It works by sweeping a line across the plane and processing the points encountered by the line in a specific order. The sweep line algorithm starts with a sorted list of input points and processes each point in order. As the sweep line passes through each point, it creates or updates the corresponding triangles in the triangulation. The algorithm maintains a data structure known as the sweep line status that stores the current state of the triangulation. The sweep line algorithm has a time complexity of n log n, where n is the number of input points. It is generally more efficient than the Bowyer-Watson algorithm for large datasets but may require additional preprocessing steps, such as sorting and building the sweep line status structure. 7.2.3 Divide and Conquer algorithm. The divide and conquer algorithm is a divide and conquer based approach for Delaunay triangulation. It works by recursively dividing the input points into smaller subsets, constructing Delaunay triangulations for each subset, and merging them to form the final triangulation. The divide and conquer algorithm provides an efficient way to compute the Delaunay triangulation, especially for large datasets. It has a time complexity of n log n and offers better stability than the Bowyer-Watson algorithm for handling degenerate cases. However, it can be more complex to implement compared to the other algorithms. 7.2.4 Comparison of different algorithms. When choosing the right algorithm for Delaunay triangulation, several factors need to be considered. Input data size. If you are dealing with a small number of input points, both the Bowyer-Watson algorithm and the sweep line algorithm can provide satisfactory performance. However, for large datasets, the sweep line algorithm or the divide and conquer algorithm may be more efficient. Degenerate cases. If your input data contains degenerate cases, such as collinear points or points on the same circle, the Bowyer-Watson algorithm may produce inaccurate results. In such cases, the sweep line algorithm or the divide and conquer algorithm can be more robust. Numerical stability. If your input data is prone to numerical instability, such as floating point round-off errors, the sweep line algorithm or the divide and conquer algorithm may yield better results than the Bowyer-Watson algorithm. Ease of implementation. The Bowyer-Watson algorithm is relatively straightforward to implement, while the sweep line algorithm and the divide and conquer algorithm require additional preprocessing steps or recursive operations. Time complexity. The Bowyer-Watson algorithm has a worst-case time complexity of n squared, the sweep line algorithm has a time complexity of n log n, and the divide and conquer algorithm has a time complexity of n log n. Consider the size of your input data and the desired performance trade-offs when selecting the algorithm. Available libraries. If you are using a specific graphics library or framework, check if it provides built-in support for Delaunay triangulation and which algorithm it uses. Utilizing the libraries can save development effort and ensure compatibility with existing code. In conclusion, the choice of the Delaunay triangulation algorithm depends on various factors, including the input data size, the presence of degenerate cases, numerical stability requirements, ease of implementation, and time complexity considerations. Understanding the strengths and weaknesses of each algorithm will help you make an informed decision and implement the most suitable algorithm for your specific application. 7.3 Performance Considerations. When implementing Delaunay triangulation in 2D graphics using C, performance considerations become crucial to ensure efficient and effective operation of the algorithm. In this section, we will explore some key factors that can impact the performance of Delaunay triangulation algorithms and discuss strategies to improve their efficiency. 7.3.1 Input data size. The size of the input data, particularly the number of points to be triangulated, greatly affects the performance of Delaunay triangulation algorithms. As the number of points increases, the computational complexity of the algorithm typically grows. Therefore, it is important to consider the scalability of the algorithm and choose an appropriate implementation based on the expected size of the input data. One way to handle large input datasets is to use spatial data structures, such as quad trees or KD trees, to partition the point set and speed up the search and insertion operations. These data structures allow for efficient spatial queries, reducing the time complexity of Delaunay triangulation algorithms. 7.3.2 Algorithm Selection. The choice of the Delaunay triangulation algorithm also impacts the performance of the implementation. Different algorithms have varying computational complexities and suitability for different types of input data. For example, the Bowyer-Watson algorithm is commonly used for general point sets, while the sweep-line algorithm is efficient when the points are sorted along a horizontal line. Understanding the characteristics of the input data and the strengths and weaknesses of different algorithms is essential for selecting the most appropriate one. Consider the trade-offs between time complexity, memory usage, and implementation complexity to find the algorithm that best fits your specific requirements. 7.3.3 Memory Management. Efficient memory management can significantly improve the performance of a Delaunay triangulation implementation. Allocating and deallocating memory dynamically can introduce overhead, especially when the algorithm requires frequent memory operations. To mitigate this, consider using object pools or pre-allocated memory buffers for frequently used data structures like triangles, edges, or points. Additionally, minimizing memory fragmentation and reducing memory overhead can also contribute to improved performance. Use memory-efficient data representations and avoid unnecessary duplication of data or excessive use of auxiliary storage. By optimizing memory usage, you can reduce memory access time and improve overall algorithm efficiency. 7.3.4 Preprocessing and postprocessing. Preprocessing the input data or optimizing the output can enhance the performance of Delaunay triangulation implementations. For example, if the input points lie in a known pattern or distribution, you may apply a preprocessing step to reorganize or sort the points, reducing the complexity of the triangulation process. Similarly, post-processing the triangulation by removing unnecessary triangles or edges can simplify the representation and improve subsequent operations. This can be achieved by identifying and eliminating triangles that violate specific criteria, e.g., small angles or long edges, resulting in a more compact and efficient triangulation. 7.3.5 Algorithmic Improvements. Beyond the considerations mentioned above, there are various algorithmic improvements that can further enhance the performance of Delaunay triangulation implementations. Some techniques include incremental updates. Rather than recomputing the entire triangulation from scratch when new points are added or removed, incremental algorithms allow for efficient updates by preserving the existing triangulation and adjusting it incrementally. This results in a significant reduction in computation time for dynamic scenarios. Multithreading and parallelization. Exploiting the parallelism inherent in Delaunay triangulation algorithms can lead to substantial performance gains, especially when operating on large datasets. Distributing the workload across multiple threads or processors can speed up the computation, but careful synchronization and load balancing are necessary to ensure correctness and efficiency. Algorithmic variance. Depending on the specific requirements of your application, you may consider optimizing the Delaunay triangulation algorithm to suit your particular use case. Modifying certain steps or adding customizations can lead to performance improvements tailored to your specific needs. It is worth noting that the performance considerations discussed here are general guidelines, and the specific optimizations applied will depend on the characteristics of the implementation, the input data, and the desired output. Profiling the implementation, benchmarking against different scenarios, and experimenting with different strategies can help identify the most effective performance optimizations for your specific use case. In the next section, we will explore how to handle degenerate cases in Delaunay triangulation, which can pose challenges to the algorithm's performance and correctness. 7.4 Handling degenerate cases. In the context of Delaunay triangulation, degenerate cases refer to scenarios where certain input data or intermediate states of the triangulation algorithm pose challenges or require special handling. Degeneracy can occur due to various factors, such as collinear points, duplicate points, or points lying on the same circumcircle. In order to ensure the correctness and stability of the Delaunay triangulation algorithm, it is crucial to properly handle these degenerate cases. In this section, we will explore common degenerate cases and discuss strategies to handle them. 7.4.1 Collinear points. One common degenerate case in Delaunay triangulation occurs when three or more input points are collinear, meaning they lie on the same line. When this happens, the triangulation algorithm may produce erroneous results, as the concept of a Delaunay triangle breaks down in such cases. To handle collinear points, several approaches can be employed. Elimination. One simple strategy is to identify and remove collinear points from the input before performing the triangulation. This can be achieved by checking if the cross product of two line segments formed by three consecutive points is 0. If the cross product is 0, it indicates collinearity, and the point can be discarded. Perturbation. Another technique to handle collinear points is to introduce a small perturbation to the point's coordinates. By slightly modifying the collinear point's positions, we can break the collinearity, ensuring the triangulation algorithm generates valid results. However, care must be taken to ensure that the perturbation is small enough to avoid introducing significant errors to the overall triangulation. Treat as boundary. In some cases, it might be necessary to retain the collinear points and treat them as boundary points rather than part of the triangulation. This approach is common when dealing with convex hull computations, as collinear points can define the boundary of the point set. 7.4.2 Duplicate points. Duplicate points, where two or more points in the input data have the same coordinates, can also cause issues in the Delaunay triangulation algorithm. Duplicate points can lead to the formation of degenerate triangles, resulting in incorrect or inefficient triangulation. To handle duplicate points, the following strategies can be employed. Point deduplication. The simplest approach is to remove duplicate points from the input before performing the triangulation. This can be achieved by maintaining a set or hash table data structure to track unique points. The duplicate points can be discarded, ensuring that only distinct points are used for the triangulation. Point rejection. Alternatively, duplicate points can be treated as invalid and rejected during the triangulation algorithm's execution. This approach requires modifying the algorithm to handle and skip duplicate points whenever encountered. 7.4.3 Points on same circumcircle. A crucial property of Delaunay triangulation is that no point should lie inside the circumcircle of any triangle in the triangulation. However, due to rounding errors or precision limitations, it is possible to encounter scenarios where points lie exactly on the same circumcircle. This can result in incorrect triangulation or even infinite loops during the flipping process. Several techniques can help manage this degenerate case. Circumcircle check. During the triangulation algorithm's execution, a circumcircle check must be performed to ensure if a point lies on the same circumcircle as any existing triangles. If a point lies on the circumcircle, a strategy such as point removal or point repositioning can be used to resolve the issue. Point removal involves discarding the problematic point from the triangulation, while point repositioning involves slightly modifying the point's coordinates to ensure it is no longer on the same circumcircle. Robust arithmetic. Using robust arithmetic techniques such as arbitrary precision arithmetic or exact geometrical predicates can significantly reduce the occurrence of points lying on the same circumcircle. By enhancing the precision of calculations, the likelihood of encountering this degenerate case can be minimized. Handling degenerate triangles. In some instances, it might be necessary to handle degenerate triangles explicitly. A degenerate triangle refers to a triangle with zero area, typically formed by three collinear points. By detecting and appropriately handling degenerate triangles, the algorithm can continue executing without producing incorrect or unexpected results. Handling degenerate cases in Delaunay triangulation is essential to ensure the accuracy and robustness of the algorithm. By employing appropriate strategies for collinear points, duplicate points, and points on the same circumcircle, we can mitigate the impact of degeneracy on the triangulation results. Careful consideration and implementation of these strategies allow for a reliable and efficient Delaunay triangulation algorithm in practical scenarios. 8. Performance optimization techniques. 8.1 Spatial data structures. One of the key factors that can greatly impact the performance of implementing Delaunay triangulation in 2D graphics is the choice of spatial data structures. Spatial data structures are designed to efficiently store and retrieve geometric objects in a spatially organized manner. By selecting and utilizing appropriate data structures, we can optimize the search and insertion operations required during the Delaunay triangulation process. Quad tree. A common spatial data structure used in the implementation of Delaunay triangulation is the quad tree. A quad tree divides the 2D space into a hierarchy of rectangular regions, forming a tree structure. Each node in the quad tree represents a region, and leaf nodes contain the actual geometric objects, in this case, the points of the triangulation. The quad tree offers efficient search operations by traversing the tree hierarchy, pruning unnecessary regions and focusing only on relevant regions during point insertion and search operations. This reduces the number of comparisons required and improves overall performance. In the Delaunay triangulation process, the quad tree can be constructed prior to the actual triangulation by recursively subdividing the input space. When inserting points, the quad tree is used to locate the region of interest, which accelerates the search for neighboring points. This allows for faster adjacency search and avoids redundant computations. KD tree. Another notable spatial data structure that can be used for implementing Delaunay triangulation is the KD tree, k-dimensional tree. The KD tree is an extension of the binary search tree, specialized for k-dimensional data, where each node represents a k-dimensional point. In the context of Delaunay triangulation, the KD tree can be utilized to efficiently search for points in the triangulation and determine the closest points to a given point. This property is useful during the incremental insertion of points in the triangulation. By using a KD tree, we can avoid unnecessary comparisons and quickly locate the nearest points required for the Delaunay property check. Similar to the quad tree, the construction of a KD tree involves recursively partitioning the input space based on the median value of the points in each dimension. This ensures a balanced tree structure and efficient traversal during point insertion and search operations. Other spatial data structures. Apart from quad tree and KD tree, there are several other spatial data structures that can be used for implementing Delaunay triangulation in 2D graphics. Some of these include R trees, BSP trees, and octrees. Each of these data structures has its own advantages and trade-offs, and their suitability depends on the specific requirements and characteristics of the input dataset. R trees, for example, are particularly effective for efficient range queries and spatial indexing of non-uniform data distributions. BSP trees can handle both planar and non-planar data efficiently and are well suited for visibility computations in computer graphics. Octrees are three-dimensional generalizations of quad trees and can be used for spatial indexing and subdivision of 3D data. When selecting a spatial data structure, it is essential to consider factors such as the characteristics of the input data, the specific operations required during Delaunay triangulation, and the performance goals of the implementation. Careful consideration of these factors will help in choosing the most appropriate spatial data structure and optimizing the performance of the Delaunay triangulation process. In conclusion, the efficient implementation of Delaunay triangulation in 2D graphics using C can be greatly enhanced by selecting and utilizing appropriate spatial data structures. The quad tree and KD tree are two widely used options that provide efficient search and insertion operations. However, other spatial data structures such as R trees, BSP trees, and octrees may also be suitable depending on the specific requirements and characteristics of the input data. By employing spatial data structures effectively, we can optimize the performance of the Delaunay triangulation algorithm, resulting in faster and more efficient 2D graphics rendering and processing. 8.2 Incremental updates and dynamic triangulation. In the previous section, we discussed the incremental Delaunay triangulation algorithm, which allows us to efficiently build a triangulation from a set of points by incrementally adding points to the existing triangulation. However, in many cases, the input data for the triangulation may not remain static. Points may need to be added, removed, or modified dynamically. This introduces the need for incremental updates to the triangulation and dynamic triangulation techniques. Incremental updates. When new points are added to an existing triangulation, we can use the incremental algorithm to insert the points efficiently. The new points are inserted into the existing triangulation without affecting the previously added points and their connectivity. The incremental algorithm ensures that the Delaunay property is maintained during the insertion process. The process of inserting a new point into an existing triangulation involves finding the triangle that contains the new point. This can be done by performing a point location query using techniques such as a brute force search, spatial data structures like quad tree or KD tree, or a navigation search algorithm like the walking algorithm. Once the containing triangle is found, we can split it into 3 smaller triangles by adding the new point and connecting it to the 3 vertices of the containing triangle. We then have to check and restore the Delaunay property by flipping any triangles that violate the property. This process continues until all the new points have been inserted into the triangulation. The incremental updates can also handle point deletions from the triangulation. When a point is deleted, we need to first find the triangle that contains the point and remove it from the triangulation. We then have to adjust the triangulation by flipping edges and merging triangles if necessary to maintain the Delaunay property. Updating the triangulation incrementally provides several advantages. Firstly, it avoids the need to rebuild the entire triangulation from scratch whenever new points are added or removed. This can save a significant amount of time and computational resources, especially for large datasets. Secondly, it allows for real-time updates, making it suitable for applications where the input data changes frequently. Dynamic triangulation. Dynamic triangulation extends the concept of incremental updates by allowing not only the insertion or deletion of points but also the modification of existing points in the triangulation. This is useful in scenarios where the input data is subject to frequent changes, such as interactive graphics applications or simulations. Modifying an existing point in the triangulation involves finding the triangle that contains the point and updating its position. Once the position is updated, we need to restore the Delaunay property by potentially flipping edges and merging triangles. Dynamic triangulation algorithms typically use efficient data structures and techniques to manage the connectivity of the triangulation. One commonly used data structure is the quad-edge data structure, which allows for fast navigation and efficient edge flipping operations. Other data structures like the DCEL, doubly connected edge list, can also be used for dynamic triangulation. The main challenge in dynamic triangulation is maintaining the performance of the algorithm despite the dynamic changes to the triangulation. As the number of points and the complexity of the triangulation increase, the dynamic updates may become computationally expensive. Therefore, optimizing the data structures and update operations is crucial for achieving acceptable performance. Efficient dynamic triangulation algorithms employ techniques such as lazy flipping, delayed retriangulation, and incremental updates to minimize the computational overhead of the updates. These techniques aim to defer expensive operations until they are absolutely necessary, reducing the overall complexity of the algorithm. In some cases, it may be beneficial to partition the input data into smaller regions and perform local updates within each region. This can help distribute the computational load and improve efficiency, especially in parallel or multi-threaded environments. Implementing incremental updates and dynamic triangulation requires careful design and consideration of the data structures and algorithms involved. It is important to strike a balance between maintaining the Delaunay property, handling dynamic changes efficiently, and optimizing performance. By using appropriate techniques and data structures, we can achieve efficient and flexible Delaunay triangulation in 2D graphics applications using the C programming language. 8.3 Parallelization and multithreading. Parallelization and multithreading techniques can significantly improve the performance of Delaunay triangulation algorithms by allowing multiple computations to be executed simultaneously. In this section, we will explore different approaches to parallelizing Delaunay triangulation algorithms and discuss their benefits and challenges. Benefits of parallelization and multithreading. Parallelization and multithreading can offer several benefits when implementing Delaunay triangulation algorithms. Increased computational speed. By dividing the triangulation process into multiple tasks and executing them in parallel, the overall computation time can be significantly reduced. This is particularly beneficial when dealing with large datasets or real-time applications where fast triangulation is crucial. Better utilization of hardware resources. Many modern computers have multi-core processors, which can execute multiple threads simultaneously. By leveraging these resources, we can fully exploit the processing power of the hardware and achieve optimal performance. Improved scalability. Parallel algorithms can scale well with increasing computational resources. As hardware becomes more powerful, the parallelized algorithm can take advantage of additional cores, leading to improved performance without the need for significant code changes. Approaches to parallelization. There are several approaches to parallelizing Delaunay triangulation algorithms. Each approach has its own advantages and challenges, and the choice of parallelization technique depends on various factors such as the algorithm used, available hardware resources, and the programming language being used. Here are some common approaches. Task-based parallelism. This approach involves dividing the triangulation process into smaller tasks that can be executed independently. Each task can be assigned to a separate thread or process, allowing them to be executed simultaneously. Task-based parallelism is suitable for algorithms that have a natural division of work, such as the divide-and-conquer algorithm. Data parallelism. In data parallelism, the triangulation algorithm operates on different portions of the dataset simultaneously. For example, the dataset can be divided into parts, and each part can be processed by a separate thread or process. This approach is commonly used when processing large datasets, where the triangulation of different data points can be performed independently. Pipeline parallelism. Pipeline parallelism involves breaking down the triangulation process into multiple stages or phases. Each stage can be executed in parallel, with the output of one stage becoming the input for the next stage. This approach is suitable for algorithms that have a sequential nature, where each stage depends on the output of the previous stage. Challenges of parallelization and multithreading. Parallelization and multithreading can introduce several challenges that need to be addressed to ensure correct and efficient execution of Delaunay triangulation algorithms. Data dependencies. When multiple threads or processes are executing simultaneously, it is crucial to handle dependencies between different tasks correctly. Care must be taken to ensure that one task does not access or modify data that is being used by another task at the same time. Synchronization mechanisms such as locks, mutexes, and barriers can be used to manage data access and ensure thread safety. Load balancing. Load balancing is the process of distributing the workload evenly across multiple threads or processes to maximize resource utilization. Uneven distribution of tasks can lead to individual threads or processes being underutilized while others are overloaded. Load balancing techniques such as task stealing, dynamic scheduling, or workload partitioning can be employed to achieve better load distribution. Overhead and synchronization. Parallelization introduces additional overhead due to the cost of thread creation, synchronization, and communication between threads or processes. It is important to carefully design and optimize the parallel implementation to minimize this overhead and ensure that the benefits of parallelization outweigh the costs. Concurrency control and thread safety. Concurrent access to shared data structures can lead to race conditions and data corruption. Proper concurrency control mechanisms, such as locks, atomic operations, or thread-safe data structures, need to be employed to ensure thread safety and prevent data inconsistencies. Parallelization in practice. The choice of parallelization technique and its implementation depend on the specific characteristics of the Delaunay triangulation algorithm being used and the available hardware and software resources. It is important to carefully analyze the algorithm and identify the parts that can be parallelized effectively. Parallelization can be achieved using low-level multi-threading APIs, such as pthreads or OpenMP, or through higher-level parallel programming frameworks like Intel Threading Building Blocks (TBB) or CUDA for GPU acceleration. These frameworks provide high-level constructs and abstractions that simplify the process of parallel programming. Before implementing parallelization, it is recommended to profile and benchmark the sequential version of the algorithm to understand its performance bottlenecks. This information can guide the parallelization effort and help identify the parts of the algorithm that will benefit the most from parallel execution. Additionally, careful consideration should be given to any potential trade-offs between accuracy and performance when parallelizing Delaunay triangulation algorithms. By effectively leveraging parallelism and multithreading, the performance of Delaunay triangulation algorithms can be significantly improved. This allows for faster and more efficient processing of 2D graphics data, making them well-suited for real-time applications, large-scale datasets, and computationally intensive tasks. 8.4 Memory Management and Storage Efficiency. Memory management and storage efficiency are crucial aspects of implementing Delaunay triangulation algorithms in 2D graphics using C. In this section, we will explore various techniques and strategies to optimize memory usage and improve the storage efficiency of our triangulation data structures. 8.4.1 Memory Allocation and Deallocation. Efficient memory allocation and deallocation can significantly impact the performance of a Delaunay triangulation implementation. Allocating memory dynamically can lead to memory fragmentation and slower runtime performance. To address these issues, it is essential to employ proper memory management techniques. One commonly used technique is to pre-allocate memory for a fixed number of points and triangles. By doing so, we can avoid frequent memory allocations and deallocations during the execution of the Delaunay triangulation algorithm. However, this approach may limit the scalability of the implementation, as it requires estimating the maximum number of points and triangles in advance. Another technique is to use memory pools or object pools. In this approach, we pre-allocate a large block of memory and manage the memory allocation and deallocation ourselves. Rather than using the default malloc and free functions, we can create custom functions that allocate and deallocate objects from the memory pool. By reusing previously allocated memory blocks, this technique can significantly reduce memory fragmentation and improve memory usage efficiency. 8.4.2 Compact Data Structures. To optimize storage efficiency, it is crucial to design compact data structures for storing the triangulation information. Reducing memory usage can improve cache performance and overall execution speed. One approach is to use compact representations for points, triangles, and edges. Instead of storing each point's individual x and y coordinates, we can exploit their locality and store them in a single array. Similarly, we can store the indices of the vertices in each triangle rather than storing the actual vertex objects. This way, we can save memory by avoiding the duplication of vertex data. Additionally, we can utilize bit-level manipulation techniques to reduce the memory footprint of the data structures. For example, instead of using an entire byte to represent a Boolean flag indicating the validity of an edge, we can use a single bit flag per edge, packed into a bit mask. By carefully designing the data structures and utilizing compact representations, we can achieve significant storage efficiency improvements. 8.4.3 Memory Reuse and Recycling. Reusing memory that is no longer in use can further enhance storage efficiency. In the context of Delaunay triangulation, we can reuse triangles and edges that have been deleted or invalidated during the algorithm's execution. Rather than immediately deallocating the memory, we can keep it in a pool or list of free objects and reuse them whenever new triangles or edges are required. This approach not only reduces memory fragmentation but also reduces the overhead of memory allocation and deallocation. 8.4.4 Garbage collection and memory cleanup. In some cases, especially when dealing with large-scale triangulations or long-running applications, memory cleanup and garbage collection may become necessary. Garbage collection involves identifying and deallocating memory that is no longer in use. One possible approach is to implement a mark-and-sweep garbage collection algorithm. This algorithm traverses the data structures, marking the objects that are still in use and subsequently deallocating the unmarked objects. While garbage collection can free up memory and improve storage efficiency, it introduces overhead in terms of execution time and computational complexity. However, it's important to note that in many cases, Delaunay triangulation algorithms do not require explicit garbage collection, as the memory usage is typically well-defined and controlled by the algorithm itself. Nevertheless, for cases where memory usage may dynamically change over time, garbage collection can be a viable option. 8.4.5 Testing and Profiling for Memory Efficiency. To ensure optimal memory management and storage efficiency, it is crucial to perform testing and profiling on the implemented Delaunay triangulation algorithm. Profiling tools can help identify bottlenecks and memory leaks, allowing us to fine-tune the memory management strategies and optimize the storage efficiency. By carefully monitoring the memory usage and perform profiling tests with different input sizes, we can gain insights into the memory requirements of the algorithm. This knowledge can guide us in making informed decisions about memory allocation strategies, data structure designs, and resource management techniques. In conclusion, memory management and storage efficiency play a vital role in the implementation of Delaunay triangulation algorithms in 2D graphics using C. By employing efficient memory allocation and deallocation techniques, designing compact data structures, reusing memory, and performing proper testing and profiling, we can enhance the overall performance and memory usage efficiency of our implementation. 9. Practical implementations of Delaunay Triangulation. 9.1 Library Overview and Features. In this section, we will provide an overview of a library for implementing Delaunay Triangulation in 2D graphics using the C programming language. This library aims to provide efficient and robust algorithms for generating Delaunay triangulations from a given set of points. We will discuss the main features of the library and highlight its advantages for developers. 9.1.1 Purpose and Goals. The purpose of this library is to provide developers with a powerful tool for implementing Delaunay triangulation in their 2D graphics applications. The main goal is to simplify the process of generating high-quality triangulations, allowing developers to focus on other aspects of their projects. 9.1.2 Key Features. The library offers several key features that make it a valuable resource for implementing Delaunay triangulation. Efficient algorithms. The library implements efficient algorithms for Delaunay triangulation, ensuring fast performance even with large input datasets. These algorithms are designed to handle various types of point distributions and can adapt to different situations. Robustness and accuracy. The library prioritizes robustness and accuracy in generating Delaunay triangulations. It handles degenerate cases and edge cases effectively, ensuring that the resulting triangulations adhere to the Delaunay property. Flexibility. The library provides flexible options for customizing the triangulation process. Developers can choose from different Delaunay triangulation algorithms depending on their specific requirements. This allows for optimization based on the characteristics of the input data and the desired output. Portability. The library is designed to be portable, allowing developers to easily integrate it into their existing C projects. It is compatible with different operating systems and can be used with various compilers without any major modifications. Memory efficiency. The library optimizes memory usage, ensuring that it operates efficiently even with limited resources. It employs data structures and memory management techniques that minimize memory footprint while maintaining performance. Simple integration. The library provides a simple and intuitive interface for integrating Delaunay triangulation into existing 2D graphics applications. It offers easy-to-use functions and data structures, allowing developers to quickly integrate Delaunay triangulation without significant learning curves. Documentation and support. The library is accompanied by comprehensive documentation, including examples and tutorials, to assist developers in understanding its features and usage. In addition, support channels are available, allowing developers to seek assistance and clarification when needed. 9.1.3 Example Use Cases. The library can be used in various applications where Delaunay triangulation is a fundamental requirement. Some examples of its use cases include mesh generation. The library can be used to generate meshes for computer graphics applications, such as terrain modeling, simulation, and 3D rendering. It provides a solid foundation for creating high-quality triangulations that accurately represent the underlying geometry. Optimization algorithms. Delaunay triangulation is widely used in optimization algorithms, such as the finite element method (FEM), where it is employed to divide a complex domain into simple subdomains. The library provides the necessary tools for creating efficient and accurate triangulations for FEM and other optimization techniques. Spatial analysis. Delaunay triangulation is utilized in spatial analysis applications, such as Voronoi diagrams and geographical data processing. The library enables developers to perform spatial analysis tasks efficiently by leveraging its robust and accurate triangulation algorithms. Graphical user interfaces. The library can be integrated into graphical user interface (GUI) frameworks to support various interactive applications. For example, it can be used to create interactive maps, image processing tools, or CAD applications that require the efficient representation of geometric data. 9.1.4 Performance considerations. The library has been designed with performance in mind, employing efficient algorithms and optimized data structures. However, it is important to consider the characteristics of the input data and the specific requirements of the application to achieve optimal performance. Factors such as the number of points, point distribution, and desired level of detail should be taken into account. For large datasets, the library provides techniques for spatial data organization, such as spatial indexing structures, to speed up search and insertion operations. These techniques allow for efficient processing of large-scale triangulations without sacrificing performance. Additionally, the library offers support for parallelization and multi-threading, enabling developers to leverage the capabilities of modern multi-core processors to accelerate the triangulation process. Conclusion. In this section, we have provided an overview of a library for implementing Delaunay triangulation in 2D graphics using C. We discussed the key features of the library, including its efficient algorithms, robustness, flexibility, portability, memory efficiency, and ease of integration. We also explored some example use cases and highlighted important performance considerations. In the next section, we will delve deeper into the usage and integration of the library. 9.2 Example Usage and Integration. Once you have implemented the Delaunay triangulation algorithm in C, you can utilize it for various applications in 2D graphics. In this section, we will explore some example usage scenarios and discuss how to integrate your implementation into different graphics libraries and frameworks. 9.2.1 Triangulating a set of points. One common task in 2D graphics is to triangulate a set of points. This can be useful for creating meshes, generating Voronoi diagrams, or performing various geometric computations. To use your Delaunay triangulation implementation, you need to pass the set of points as input and obtain the resulting triangulation as output. Here is an example of how you could use your implementation to triangulate a set of points using the Bowyer-Watson algorithm. Hashtag include, Delaunay, H. Int main. Create an array of points equals 0.0, 0.0, 1.0, 0.0, 0.5, 1.0, 0.2, 0.3. Add more points as needed. Compute the Delaunay triangulation. Triangles equals Delaunay _ triangulation points, size of point. Access and process the resulting triangles for int I equals 0, I less than num _ triangles, I plus triangle equals triangles, I process the triangle data. Clean up the memory used by the triangulation result free triangles. Return 0. 9.2.2 Integration with graphics libraries. Integrating your Delaunay triangulation implementation into existing graphics libraries can significantly enhance their capabilities. By incorporating triangulation functionality, you enable users to perform complex operations such as mesh generation, terrain analysis, or 2D simulations. To integrate your implementation with a graphics library, you need to understand the library's data structures and rendering pipeline. Most graphics libraries provide APIs to work with geometric primitives, such as points, lines, and triangles, which align well with the output of the Delaunay triangulation algorithm. Here's an example of how you can integrate your implementation with a popular graphics library, OpenGL. Hashtag include less than GL, H greater than hashtag include, Delaunay, H. Void render _ triangles, int num _ triangles. GL begin, GL _ triangles. For int I equals 0, I less than num _ triangles, I plus triangle equals triangles, I. Render each vertex of the triangle GL vertex 2F triangle, P1, X, triangle, P1, Y GL vertex 2F triangle, P2, X, triangle, P2, Y GL vertex 2F triangle, P3, X, triangle, P3, Y. Glend. Int main. Create an array of points equals 0.0, 0.0, 1.0, 0.0, 0.5, 1.0, 0.2, 0.3. Add more points as needed. Compute the Delaunay triangulation. Triangles equals Delaunay _ triangulation points, size of point. Initialize graphics library e.g., OpenGL. Render the triangles render _ triangles, num _ triangles. Clean up the memory used by the triangulation result free triangles. Shut down the graphics library. Return 0. 9.2.3 Interfacing with other graphics libraries. In addition to integrating your implementation into graphics libraries, you may also need to interface with other graphics tools and frameworks. This could involve exchanging data with vector graphics editors, mesh processing libraries, or 2D game engines. To interface your Delaunay triangulation implementation with other graphics libraries, you typically need to conform to their data formats or APIs. This might involve converting data between different formats, such as converting your internal point representation to the format expected by the target library. The specific details of interfacing will vary depending on the library or tool you are working with. However, by understanding the input and output requirements of the target library, you can adapt your implementation accordingly. 9.2.4 Case Studies and Real-World Applications. To gain further insights into practical usage and integration of Delaunay triangulation, it can be helpful to explore case studies and real-world applications. By examining how others have employed Delaunay triangulation in their projects, you can learn from their experiences and apply those lessons to your own work. Some common real-world applications of Delaunay triangulation include terrain generation for computer graphics and game development, surface mesh generation for finite element analysis or computational fluid dynamics simulations, Voronoi diagram generation for proximity analysis in fields like geospatial analysis and wireless network planning, Delaunay refinement for improving the quality of triangular meshes. By studying case studies and real-world applications, you can gain insights into best practices, optimization techniques, and potential challenges associated with using Delaunay triangulation in specific domains or contexts. In the next section, we will explore advanced topics in Delaunay triangulation, including boundary constraints, mesh generation, Voronoi diagrams, and higher dimensional triangulations. 9.3 Interfacing with other graphics libraries. In many practical applications, the need to interface with other graphics libraries is quite common when implementing Delaunay triangulation in 2D graphics using C. These libraries provide a wide range of functionalities and tools that can greatly enhance the capabilities and performance of your Delaunay triangulation implementation. This section explores the process of integrating your Delaunay Triangulation code with other graphics libraries to leverage their features and benefits. 9.3.1 Choosing the right graphics library. Before diving into the details of interfacing, it is crucial to choose the right graphics library that aligns with the requirements and goals of your application. The choice of library depends on factors such as the programming language compatibility, operating system support, performance requirements, ease of use, and availability of advanced graphics features. For C-based applications, some popular graphics libraries that can be considered are SDL, Simple Direct Media Layer. SDL is a powerful cross-platform development library that provides low-level access to audio, keyboard, mouse, joystick, and graphics hardware. It offers an easy-to-use interface and supports various platforms, making it a good choice for creating interactive applications. OpenGL. OpenGL is an industry-standard graphics API that enables high-performance 2D and 3D graphics rendering across multiple platforms. Its versatility and extensive support from hardware vendors make it suitable for a wide range of applications. DirectX. DirectX is a collection of APIs developed by Microsoft, primarily for Windows-based systems. It offers features for multimedia and game development, including high-performance 2D and 3D graphics rendering. These are just a few examples of graphics libraries, and depending on your specific requirements, there may be other suitable options available. It is essential to carefully evaluate and select the library that best fits your application's needs. 9.3.2 Interface Design. Once you have chosen the appropriate graphics library, the next step is to design and implement an interface layer that bridges your Delaunay Triangulation code with the graphics library. The interface layer acts as a translator, converting the internal data structures used in your Delaunay Triangulation implementation to the format expected by the graphics library. A well-designed interface should provide an abstraction layer that encapsulates the intricacies of the graphics library and exposes a clean, user-friendly interface for your Delaunay Triangulation code. The interface layer should handle tasks such as converting points, triangles, and edges to the appropriate data structures used by the graphics library, performing coordinate system transformations if necessary, and rendering the triangulation on the screen. 9.3.3 Data Conversion. One of the critical aspects of interfacing with a graphics library is converting the data structures used in your Delaunay Triangulation implementation to the format expected by the library. This conversion process typically involves mapping the internal representation of points, triangles, and edges to the corresponding data structures used by the graphics library. For example, if your Delaunay Triangulation implementation uses a custom point struct to represent points, you may need to convert this struct to the format expected by the graphics library, such as a vertex object or coordinate tuple. Similarly, the triangle and edge data structures used internally may need to be converted to the equivalent graphics library representations, like a polygon or line segment. Care should be taken to ensure that the data conversion is efficient and accurate. Inefficient data conversion can introduce performance bottlenecks, while inaccurate conversion may result in visual artifacts or incorrect rendering of the triangulation. 9.3.4 Rendering the triangulation. Once the data conversion is complete, the next step is to render the triangulation using the capabilities provided by the chosen graphics library. The process of rendering involves specifying the appropriate drawing commands and parameters to create the visual representation of the triangulation. The specific rendering techniques and APIs provided by the graphics library will depend on the library itself. Some common techniques include rendering each triangle as a filled polygon, rendering the edges as lines or line segments, and adding colors or textures to enhance the visual representation. It is advisable to explore the documentation and tutorials provided by the graphics library to gain a deep understanding of its rendering capabilities and achieve the desired visual effects for your Delaunay Triangulation. 9.3.5 Interaction and User Interface. In many cases, the integration of Delaunay Triangulation with a graphics library involves not only visualizing the triangulation but also providing interactive functionality and user interface elements. The graphics library can help facilitate user interaction by supporting events, such as mouse clicks or keyboard input, and providing facilities for handling user actions. Some possible interactions that can be implemented include allowing the user to add or remove points interactively, zooming and panning on the triangulation, highlighting specific triangles or edges based on user selection, and displaying additional information about the triangles or points. The graphics library's event handling mechanism should be utilized to detect user actions and update the triangulation accordingly. This may involve modifying the Delaunay Triangulation data structure and triggering the necessary updates and redraws. 9.3.6 Performance Considerations. When interfacing with other graphics libraries, it is crucial to consider the performance implications of your implementation. Graphics libraries often provide various optimizations and rendering techniques to improve performance, such as vertex buffers, display lists, and shader programs. To achieve optimal performance, you should leverage these advanced features provided by the graphics library and ensure efficient data transfer between your Delaunay Triangulation implementation and the graphics library. Additionally, consider the impact of the triangulation size on rendering performance. Large triangulations with a high number of triangles may result in decreased performance, especially if complex rendering techniques are employed. It may be beneficial to use techniques like level of detail rendering or adaptive rendering to improve performance without sacrificing visual fidelity. 9.4 Case Studies and Real-World Applications. In this section, we will explore some case studies and real-world applications where Delaunay triangulation has proved to be a valuable tool in 2D graphics. We will examine the use of Delaunay triangulation in various domains and highlight its benefits and contributions in each case. 9.4.1 Terrain Modeling and Visualization. One of the primary applications of Delaunay triangulation in 2D graphics is terrain modeling and visualization. By utilizing elevation data points, the Delaunay triangulation algorithm can generate a mesh that accurately represents the underlying terrain. This allows for the creation of realistic 3D representations of landscapes and terrains. By triangulating the elevation data points, the resulting mesh can be used to generate smooth surfaces that accurately capture the shape and contour of the terrain. This is particularly useful in fields such as Geographic Information Systems (GIS), computer-aided design (CAD), and video game development, where terrain modeling plays a crucial role. 9.4.2 Mesh Generation for Finite Element Analysis. Finite element analysis (FEA) is a numerical method used in engineering and physics to approximate the behavior of complex systems. In FEA, mesh generation is a critical step in creating a discretized representation of the domain being analyzed. Delaunay triangulation can be utilized to generate high-quality meshes that accurately capture the geometry of the domain. By leveraging the Delaunay triangulation algorithm, engineers and scientists can efficiently generate meshes with well-shaped elements. Having high-quality meshes improves the accuracy and reliability of the FEA results. This application is particularly relevant in areas such as structural analysis, fluid dynamics, and electromagnetic simulations. 9.4.3 Image Processing and Computer Vision. Delaunay triangulation finds applications in image processing and computer vision tasks. In image processing, Delaunay triangulation can be used to generate an image mosaic by blending multiple images together seamlessly. Triangulating key features in the images allows for smooth transitions and realistic stitching. Furthermore, Delaunay triangulation has been widely used in computer vision algorithms for tasks like shape analysis, object recognition, and motion tracking. By triangulating a set of key points or features in an image, it becomes possible to extract meaningful information and analyze the visual data efficiently. 9.4.4 Surface Reconstruction and 3D Scanning. In the realm of surface reconstruction and 3D scanning, Delaunay triangulation plays a crucial role in generating realistic and accurate models from point cloud data. Point cloud data obtained from 3D scanners or other measurement devices can be processed using the Delaunay triangulation algorithm to reconstruct the underlying surface. By triangulating the points and connecting them to form triangles, the resulting mesh represents the surface of the scanned object. This surface mesh can then be further processed to remove noise, fill in gaps, or refine the model. This application finds utilization in fields such as reverse engineering, cultural heritage preservation, and quality control in manufacturing. 9.4.5 Computational Geometry and Spatial Analysis. Delaunay triangulation is a fundamental algorithm in computational geometry, providing a powerful framework for solving various spatial analysis problems. It facilitates applications such as spatial interpolation, feature extraction, proximity analysis, and Voronoi diagram generation. Spatial interpolation techniques, such as inverse distance weighting and kriging, often rely on Delaunay triangulation to interpolate values from scattered data points. Similarly, feature extraction algorithms can utilize the connectivity information provided by Delaunay triangulation to identify patterns or structures in spatial datasets. 9.4.6 Game Development and Computer Graphics. In the field of game development and computer graphics, Delaunay triangulation finds application in various areas. Game terrain generation algorithms often employ Delaunay triangulation to create realistic landscapes and terrains. Moreover, Delaunay triangulation can aid in collision detection, pathfinding, and procedural content generation. Additionally, Delaunay triangulation is used in creating smooth and visually pleasing meshes for 3D models. By generating a well-structured mesh, the resulting model can be efficiently rendered and animated in real-time applications such as video games, virtual reality, and computer-generated movies. These case studies highlight the versatility and practicality of Delaunay triangulation in numerous domains. From terrain modeling to computer graphics and spatial analysis, the algorithm provides a valuable tool for solving complex visual and geometric problems. By understanding the real-world applications of Delaunay triangulation, developers can leverage its power to create innovative and efficient solutions in 2D graphics. 10. Advanced Topics in Delaunay Triangulation. 10.1 Boundary Constraints and Convex Hulls. In the previous sections, we have discussed the basic concepts and algorithms of Delaunay triangulation. However, in many practical scenarios, we may need to impose certain boundary constraints on the triangulation or derive additional geometric information from it. In this section, we will explore the concepts of boundary constraints and convex hulls in the context of Delaunay triangulation. Boundary constraints. In some applications, it is necessary to enforce specific geometric constraints on the triangulation boundaries. For example, we might want to ensure that certain points lie on the border of the triangulation or that the triangulation respects a given outline shape. In such cases, we need to incorporate these constraints into the Delaunay triangulation process. One common way to handle boundary constraints is by introducing additional virtual points along the desired boundaries. These virtual points act as placeholders and are treated as regular points during the triangulation process. By ensuring the inclusion of these boundary points, we can achieve the desired geometric constraints. To incorporate boundary constraints, we first define the virtual points on the boundary. These points can be manually specified or generated algorithmically based on the desired constraint. Once these points are defined, we can proceed with the regular Delaunay triangulation algorithm, treating the virtual points as any other input points. The resulting triangulation will naturally follow the desired boundary constraints. It's important to note that while the virtual points are included in the triangulation, they may not necessarily be part of the final output if they lie within the interior of the convex hull. Therefore, it might be necessary to filter out the virtual points from the triangulation output to obtain the desired boundary triangulation. Convex hulls. The convex hull of a set of points is the smallest convex polygon that encloses all the points. In the context of Delaunay triangulation, the convex hull plays an important role as it defines the outer boundary of the triangulation. The convex hull can provide valuable information for further analysis or rendering purposes. To compute the convex hull of a set of points, there are several well-known algorithms available, such as the gift wrapping algorithm, Graham's scan, and the quick hull algorithm. These algorithms take a set of points as input and return the vertices of the convex hull in a counterclockwise order. Once we have the convex hull, we can integrate it with the Delaunay triangulation output to obtain the final boundary triangulation. By connecting the vertices of the convex hull with the Delaunay triangles that enclose them, we can ensure that the triangulation follows the shape of the convex hull. In some cases, the convex hull itself may be of interest, and the triangulation can be discarded. For example, when dealing with shape recognition or collision detection, the convex hull can provide a simplified representation of the original point set, facilitating efficient computations. It's worth noting that when dealing with complex or concave boundaries, the convex hull may not be sufficient. In such cases, advanced techniques like alpha shapes or the Voronoi diagram can be used to capture the desired boundary shape with more precision. Conclusion. Boundary constraints in convex hulls are important concepts in the context of Delaunay triangulation. By incorporating boundary points and connecting them with the Delaunay triangles, we can enforce geometric constraints on the triangulation boundaries. Additionally, the convex hull provides the outer boundary of the triangulation and can be useful for further analysis or simplification purposes. In the next section, we will explore the topic of Delaunay refinement and mesh generation, which involves optimizing the initial triangulation to achieve specific quality criteria. 10.2 Delaunay refinement and mesh generation. Delaunay refinement is a technique used to improve the quality of a Delaunay triangulation by iteratively adding and removing points in order to optimize certain properties of the mesh. This process is essential in many applications, such as computer graphics, computational fluid dynamics, and finite element analysis, where a high-quality mesh is required for accurate simulations and visualizations. Overview of Delaunay refinement. The goal of Delaunay refinement is to create a mesh that satisfies certain criteria, such as maximizing the minimum angle or minimizing the aspect ratio of the triangles. The refinement process starts with an initial Delaunay triangulation and then iteratively modifies the mesh until the desired criteria are met. The refinement algorithm typically begins by identifying triangles that do not meet the desired quality criteria. This can be done by computing a metric for each triangle, such as the minimum angle or aspect ratio, and comparing it to a threshold. Once the problematic triangles are identified, the refinement algorithm suggests a local modification to the mesh to improve the quality. There are multiple approaches to Delaunay refinement, each with its own advantages and trade-offs. In one common approach, known as edge flipping, the algorithm identifies edges that violate the Delaunay criterion and flips them to improve the mesh connectivity. This process continues until no further improvement can be achieved. Another approach, called point insertion, involves adding new points to the mesh strategically in order to create triangles with better quality. These points are typically inserted at the centroid of a set of adjacent triangles or along edges that need improvement. This process is repeated until a satisfactory mesh is obtained. Implementation considerations. Implementing Delaunay refinement requires careful consideration of various factors. One important factor is the choice of data structures to represent the mesh efficiently. Common data structures used for mesh representation include arrays, linked lists, and half-edge data structures. These data structures should support fast insertion and deletion operations, as they are frequently used during the refinement process. Efficient point location is another crucial aspect of Delaunay refinement. Point location refers to the task of determining which triangle contains a given point. Various techniques, such as efficient search trees like KD trees or spatial partitioning structures like quad trees, can be employed to achieve fast point location. The choice of quality metrics also plays a significant role in the refinement process. Different applications have different requirements, and the choice of quality metrics should align with the specific needs of the problem domain. Common quality metrics include minimum angle, maximum edge length, aspect ratio, and triangle area. Additionally, the termination criteria for the refinement process must be defined. This could be based on reaching a specific quality threshold or achieving a certain number of refinement iterations. It is important to balance the desire for high-quality meshes with computational efficiency, as excessive refinement can lead to excessive computation time. Challenges and limitations. Implementing Delaunay refinement poses several challenges and limitations. One challenge is ensuring the correctness of the refinement algorithm, as incorrect modifications to the mesh can lead to invalid triangles or inconsistent connectivity. Extensive testing and debugging are necessary to ensure the algorithm produces a valid and robust mesh. Another challenge is dealing with degenerate cases, such as points lying on a straight line or in a concave configuration. Handling these cases requires special treatment to prevent the refinement algorithm from producing low-quality or invalid meshes. This often involves detecting and resolving such degeneracies before or during the refinement process. The efficiency of the refinement algorithm is also an important consideration. In practice, the size of the input data and the complexity of the refinement criteria can significantly impact the running time of the algorithm. Therefore, implementing efficient data structures, optimized algorithms, and parallel computing techniques can help alleviate performance bottlenecks. It is worth noting that Delaunay refinement is not always necessary or beneficial for all applications. In some cases, a straightforward Delaunay triangulation may be sufficient for the desired analysis or visualization tasks. The decision to incorporate Delaunay refinement should be based on the specific needs of the application and the trade-offs between computational cost and mesh quality improvement. Conclusion. Delaunay refinement is a vital technique for improving the quality of a Delaunay triangulation in various applications. It involves iteratively modifying the mesh to optimize specific criteria, such as minimum angle or aspect ratio. Implementing Delaunay refinement requires careful consideration of data structures, point location techniques, quality metrics, termination criteria, and handling of degenerate cases. Despite the challenges and limitations, Delaunay refinement offers a powerful tool for generating high-quality meshes in 2D graphics applications implemented using the C programming language. 10.3 Voronoi diagrams and Delaunay duals. The Voronoi diagram is closely related to the Delaunay triangulation and provides useful geometric information about the input point set. In this section, we will explore the concept of Voronoi diagrams and their relationship with Delaunay duals. 10.3.1 Introduction to Voronoi diagrams. A Voronoi diagram, also known as a Voronoi tessellation or Voronoi decomposition, is a partitioning of space into regions based on proximity to a set of input points. Each region of the Voronoi diagram is defined as a set of points that are closer to a particular input point than to any other input points. The Voronoi diagram can be seen as a collection of polygons, where each polygon represents the region of space that is closest to a specific input point. These polygons are called Voronoi cells or Voronoi regions. The Voronoi diagram has various applications in different areas, including computer graphics, computational geometry, physics, and pattern recognition. It can be used for proximity analysis, nearest neighbor search, spatial interpolation, and mesh generation, among other tasks. 10.3.2 Constructing the Voronoi diagram. The Voronoi diagram can be constructed from the Delaunay triangulation. Given a set of input points, we can first compute the Delaunay triangulation using any of the algorithms discussed earlier. Once we have the Delaunay triangulation, we can derive the Voronoi diagram from it. To construct the Voronoi diagram from the Delaunay triangulation, we assign each triangle of the Delaunay triangulation to the corresponding Voronoi region. The Voronoi region associated with each triangle consists of all the points that are closer to the associated input point than to any other input points. This can be achieved by finding the circumcenter of each triangle in the Delaunay triangulation. The circumcenter of a triangle is the center of the circle that passes through all the vertices of the triangle. The Voronoi region associated with a triangle is then defined as the set of points that are closer to the circumcenter of the triangle than to any other circumcenters. By connecting the circumcenters of adjacent triangles in the Delaunay triangulation, we can obtain the boundaries of the Voronoi regions. These boundaries are typically composed of line segments, which represent the edges of the Voronoi diagram. 10.3.3 Delaunay duals. In addition to the Voronoi diagram, the Delaunay triangulation also has a dual structure known as the Delaunay dual. The Delaunay dual is a graph representation of the Delaunay triangulation, where the nodes represent the input points and the edges represent the adjacent triangles in the Delaunay triangulation. The Delaunay dual provides a useful way to visualize the connectivity of the Delaunay triangulation. Each triangle in the Delaunay triangulation corresponds to a node in the Delaunay dual, and the edges in the Delaunay dual connect the nodes corresponding to adjacent triangles. The Delaunay dual can be obtained by drawing an edge between the circumcenters of adjacent triangles in the Delaunay triangulation. This creates a graph structure that represents the connectivity of the triangles in the Delaunay triangulation. The Delaunay dual is particularly useful in applications where the connectivity of the triangles is important, such as mesh generation and network analysis. It provides a compact representation of the Delaunay triangulation while preserving important geometric properties. 10.3.4 Practical applications of Voronoi diagrams and Delaunay duals. The Voronoi diagram and the Delaunay dual have numerous practical applications in various fields. Some of the common applications include proximity analysis. Voronoi diagrams can be used to analyze the proximity of points in a given dataset. For example, in location-based services, Voronoi diagrams can be used to determine the nearest location to a given point. Nearest neighbor search. Voronoi diagrams are also useful for performing nearest neighbor searches efficiently. By associating each point with its corresponding Voronoi region, we can quickly determine the nearest neighbor of a given point. Spatial interpolation. In geostatistics, Voronoi diagrams are used for spatial interpolation, where values at unknown locations are estimated based on the values at neighboring known locations. The Voronoi diagram helps to define the spatial neighborhood around each unknown point. Mesh generation. The Voronoi diagram can be utilized for generating high-quality meshes in computer graphics and computational physics. The Voronoi regions define the shape and connectivity of the mesh elements, allowing for efficient simulation and visualization. Network analysis. The Delaunay dual can be used for network analysis and planning. By considering the connectivity of the triangles in the Delaunay triangulation, one can determine the optimal routes and connections in a network. These are just a few examples of the practical applications of Voronoi diagrams and Delaunay duals. These concepts have much broader applicability, and their versatility makes them valuable tools in various domains. In the next section, we will dive into higher dimensional Delaunay triangulation and explore its significance in multidimensional space. 10.4 Higher dimensional Delaunay triangulation. So far, we have discussed the fundamentals of Delaunay triangulation in the context of 2D graphics. However, Delaunay triangulation is not limited to 2D spaces and can be extended to higher dimensions. In this section, we will explore the concept of higher dimensional Delaunay triangulation and its applications. 10.4.1 Understanding higher dimensional spaces. Before delving into higher dimensional Delaunay triangulation, let's briefly understand the notion of higher dimensional spaces. In a 2D space, we use two coordinates x, y to represent a point. Similarly, in a 3D space, we use three coordinates x, y, z to represent a point. In general, a higher dimensional space refers to a space with more than 3 dimensions, where each point is represented by a set of coordinates. 10.4.2 Extension of Delaunay triangulation to higher dimensions. The principles of Delaunay triangulation can be extended to higher dimensional spaces. Instead of triangles, higher dimensional Delaunay triangulation involves the construction of simplexes, which are higher dimensional counterparts of triangles. In 2D, triangles are formed by connecting 3 points, while in 3D, tetrahedra are formed by connecting 4 points. In higher dimensions, the Delaunay triangulation algorithm becomes more complex, as the number of possible connections increases exponentially with the number of dimensions. However, the fundamental concept remains the same: the Delaunay property must be satisfied for all the constructed simplexes. That is, for every simplex, there should be no other point inside its circumhypersphere. To construct higher dimensional Delaunay triangulation, various algorithms have been proposed, such as the Bowyer-Watson algorithm, the incremental algorithm, and the divide-and-conquer algorithm. These algorithms are adaptations of their 2D counterparts and aim to construct a valid higher dimensional Delaunay triangulation efficiently. 10.4.3 Applications of higher dimensional Delaunay triangulation. Higher dimensional Delaunay triangulation finds applications in various fields, including computer graphics, computational geometry, finite element analysis, and mesh generation. Here are a few examples of its applications. Mesh generation in finite element analysis. Finite element analysis (PE) is a numerical method used to approximate solutions for differential equations in engineering and physics. Higher dimensional Delaunay triangulation is essential for mesh generation in PE. By triangulating a higher dimensional space, a mesh is created to represent the geometry of the problem domain. The resulting mesh is used to discretize the problem, allowing the application of numerical methods to obtain approximate solutions. Surface reconstruction. In computer graphics and computer vision, surface reconstruction refers to the process of obtaining a 3D surface representation from unorganized point clouds or 3D data. Higher dimensional Delaunay triangulation can be used to construct a surface mesh that represents the underlying structure of the data. This surface mesh can be further refined and processed to create realistic 3D models. Geometric modeling. Geometric modeling encompasses a range of techniques used to represent and manipulate geometric shapes. Higher dimensional Delaunay triangulation can be employed in the generation of complex geometric models that are beyond 3D. By extending the principles of Delaunay triangulation, it becomes possible to partition and represent shapes in higher dimensional spaces, enabling accurate modeling and analysis. Conclusion. In this section, we explored the concept of higher dimensional Delaunay triangulation and its applications. We learned that the principles of Delaunay triangulation can be extended to higher dimensions by constructing simplexes instead of triangles. We also discussed the applications of higher dimensional Delaunay triangulation in mesh generation, surface reconstruction, and geometric modeling. By understanding and implementing higher dimensional Delaunay triangulation, you can unlock a whole new range of possibilities in various domains. 11. Troubleshooting and debugging. 11.1 Common mistakes and errors. Implementing Delaunay triangulation in 2D graphics can be a complex task, and even experienced programmers can make mistakes or encounter errors during the development process. In this section, we will discuss some common mistakes and errors that you may come across when implementing Delaunay triangulation in 2D graphics using C. Undefined behavior and segmentation faults. One of the most common errors in any programming task is undefined behavior. This occurs when the program accesses memory that it is not allowed to access, leading to unpredictable results. In the context of Delaunay triangulation, undefined behavior can often manifest as segmentation faults. To avoid such errors, it is crucial to carefully manage memory allocations and deallocations. Ensure that you free any dynamically allocated memory when it is no longer needed. Additionally, be mindful of array bounds and index calculations to prevent buffer overflows. Incorrect implementation of geometric primitives. Delaunay triangulation relies on various geometric primitives such as points, triangles, and edges. Implementing these primitives incorrectly can lead to erroneous triangulations. For example, when creating a new triangle, ensure that the vertices are stored in a consistent order and that the triangle's edges are correctly defined. Incorrect orientation or missing edges can result in invalid triangulations. Similarly, when constructing and updating the triangulation, ensure that the points are inserted in the correct order. Incorrect point insertion can lead to overlapping or improperly connected triangles. Numerical precision and floating point errors. Numerical precision can be a challenge when working with floating point numbers in geometric computations. Even small errors in floating point calculations can accumulate and result in incorrect triangulations. To mitigate these errors, consider using fixed-point arithmetic or high-precision libraries for geometric calculations. Additionally, be cautious while comparing floating point numbers for equality. Instead, use an epsilon value to determine if two numbers are close enough. Invalid initialization and initialization order. The correct initialization of data structures and variables is essential for a robust Delaunay triangulation implementation. Failing to initialize variables or initializing them in the wrong order can lead to unpredictable behavior. Ensure that all relevant data structures and variables are properly initialized before using them. In some cases, it may be necessary to initialize certain data structures iteratively according to the requirements of the algorithm being used. Incorrect handling of degenerate cases. Delaunay triangulation algorithms may encounter degenerate cases, such as collinear points, coincident points, or points lying on the boundary of the triangulation. Failing to handle these cases properly can result in incorrect triangulations or even algorithmic failures. To handle degenerate cases correctly, consider implementing special checks and conditions within your algorithm. For example, you may need to detect collinear points and adjust the triangulation accordingly. Additionally, be mindful of points lying on the boundary of the triangulation and ensure that they are properly handled during the insertion and removal of points. Insufficient testing and validation. Testing and validating your Delaunay triangulation implementation thoroughly is crucial to ensure its correctness and reliability. Failing to perform sufficient testing can result in undetected errors that may cause issues later on. Create a comprehensive suite of test cases that cover various scenarios, including edge cases and common input data patterns. Use known inputs and expected outputs to verify the correctness of your implementation. Additionally, visualize the triangulation output to visually inspect and validate its accuracy. Lack of error handling and reporting. When working on a complex task like Delaunay triangulation, it is important to include proper error handling and reporting mechanisms. Failing to handle errors effectively can make debugging and identifying issues more challenging. Implement error handling mechanisms such as error codes, exception handling, or error logs to provide informative feedback in case of errors or abnormal behavior. This will aid in debugging and provide insights into the cause of the errors. Lack of documentation and code comments. Clear and comprehensive documentation is vital for understanding and maintaining your Delaunay triangulation implementation. Failing to document your code adequately can result in confusion and difficulty in troubleshooting. Include comments in your code to explain the purpose of functions, algorithms, and data structures. Clearly document any assumptions or limitations of your implementation. This will help others understand your code and improve collaboration and maintainability. Inefficient algorithms or data structures. Efficiency is an important aspect of any implementation, including Delaunay triangulation. Using inefficient algorithms or data structures can result in poor performance and unnecessary computational overhead. Carefully choose the appropriate algorithm and data structures for your specific requirements. Consider factors such as memory consumption, computational complexity, and expected input size. Implement optimizations and techniques discussed in previous chapters, such as spatial data structures or parallelization, to improve performance when applicable. In summary, implementing Delaunay triangulation in 2D graphics can be challenging, and it is common to encounter errors and mistakes during the development process. By being aware of these common pitfalls and implementing proper error handling, thorough testing, and efficient algorithms, you can mitigate these issues and create a robust and reliable Delaunay triangulation implementation. 11.2 Debugging Techniques and Tools. Debugging is an essential part of the software development process, and implementing Delaunay triangulation in 2D graphics using C is no exception. In this section, we will explore various debugging techniques and tools that can help you identify and fix issues in your implementation. 11.2.1 Debugging Techniques. Logging and Printing. One of the simplest and most effective debugging techniques is the use of logging and printing statements. By strategically placing print statements at key points in your code, you can output valuable information such as variable values, function calls, and error messages. This can help you trace the execution flow and identify potential issues. When logging or printing, it's crucial to choose the appropriate level of detail. Too much output can overwhelm you with information, while too little may not provide enough insight. Consider using different log levels, e.g., debug, info, warning, error, to control the verbosity of your output. Code reviews and pair programming. Getting a fresh pair of eyes on your code can be immensely helpful in identifying bugs and improving the quality of your implementation. Conducting code reviews with your team or pairing up with another developer can uncover issues that you might have missed. Two heads are often better than one when it comes to debugging complex algorithms like Delaunay Triangulation. During code reviews, pay attention to code readability, proper implementation of algorithms, error handling, and potential performance bottlenecks. Encourage constructive feedback and open discussions with your peers to learn from their experiences and perspectives. Step-by-step execution. Another effective debugging technique is to step through your code and observe its execution step by step. Most modern integrated development environments (IDEs) provide debugging tools that allow you to set breakpoints, inspect variable values, and execute code line by line. By observing the state of your program at different points, you can gain insights into how the algorithm is working and spot any anomalies. Take advantage of the debugging features provided by your IDE and familiarize yourself with the available tools. Learn how to set breakpoints, step into or over function calls, and examine variable values in real time to gain a deeper understanding of the code execution flow. 11.2.2 Debugging Tools. Memory debuggers. Memory-related bugs can be particularly challenging to diagnose and fix. Memory leaks, invalid memory accesses, and other memory-related issues can lead to crashes, incorrect results, or undefined behavior. Using memory debuggers can help you identify and resolve these problems. Tools like Valgrind and Address Sanitizer (ASAN) can identify memory leaks, buffer overflows, use after free errors, and other memory-related issues. These tools track memory allocations and deallocations, detect memory access errors, and provide detailed reports to help you pinpoint the problematic areas. Profilers. Profiling tools enable you to analyze the runtime characteristics of your code, helping you identify bottlenecks and performance issues. Profilers gather information about the execution time of functions, memory usage, and other critical metrics. In the context of Delaunay triangulation, profiling can help you identify computationally expensive operations or areas where unnecessary memory allocations occur. By profiling your code, you can optimize critical sections, reduce memory usage, and improve overall performance. Popular profilers for C include GNuGProfessor, Perf, and Valgrind's Calgrind tool. These tools provide detailed reports, including function call graphs, runtime statistics, and memory profiling information, enabling you to make data-driven optimizations. Unit testing frameworks. Unit testing is an invaluable technique for verifying the correctness of your code and ensuring that it produces expected results. By writing tests that cover different edge cases and scenarios, you can identify and fix bugs early in the development process. Unit testing frameworks such as CPP-U-Test, Unity, and C-Unit provide a structured approach to writing and executing tests. These frameworks simplify the process of defining test cases, handling assertions, and generating test reports. By regularly running your tests, you can quickly identify regressions and validate the correctness of your implementation. Conclusion. Debugging is an iterative and essential process in software development. By utilizing proper techniques and tools, you can identify and fix issues in your Delaunay triangulation implementation effectively. Logging and printing statements, code reviews, step-by-step execution, memory debuggers, profilers, and unit testing frameworks are valuable resources that can significantly simplify the debugging process. Take the time to invest in your debugging skills and become familiar with the tools available. A well-debugged implementation will not only result in more robust and reliable code but also enhance your understanding of the intricacies of Delaunay triangulation and 2D graphics in general. Remember, bugs are a natural part of development, and by employing these techniques and tools, you can find and squash them more effectively and efficiently. 11.3 Optimizing performance and memory usage. When implementing Delaunay triangulation in 2D graphics using C, it is essential to consider the performance and memory usage of the algorithm. Optimization techniques can greatly improve the efficiency of the triangulation process and ensure that it can handle large datasets in a reasonable amount of time. In this section, we will explore some strategies to optimize the performance and memory usage of your Delaunay triangulation implementation. 11.3.1 Data structure selection. One crucial aspect of optimizing performance and memory usage is selecting appropriate data structures for storing and manipulating the triangulation data. Efficient data structures can significantly impact the overall performance of the algorithm. There are several data structures commonly used in Delaunay triangulation implementations, such as linked lists, arrays, and hash maps. Each data structure has its advantages and disadvantages in terms of memory usage and access time. For efficient searching and insertion operations, consider using data structures that provide fast lookup times, such as hash maps or balanced search trees. These data structures allow for quick point location and insertion, which are key operations in the Delaunay triangulation algorithm. Additionally, optimizing memory usage can be achieved by minimizing the storage requirements for each element in the data structures. For example, instead of storing the full coordinates of each point, you can use relative coordinates or integer-based representations to save memory. 11.3.2 Algorithmic optimization. Besides data structure selection, various algorithmic optimizations can significantly impact the performance of your Delaunay triangulation implementation. 11.3.2.1 Incremental updates. The incremental Delaunay triangulation algorithm provides a way to update an existing triangulation efficiently when new points are added or removed. By taking advantage of this technique, you can avoid reconstructing the entire triangulation from scratch, saving a significant amount of computational time. When adding new points, use the incremental algorithm to find the affected triangles and update the triangulation accordingly. Similarly, when removing points, ensure that the triangulation remains valid by adjusting the surrounding triangles. 11.3.2.2 Multithreading and parallelization. To further optimize performance, consider implementing parallelization or multithreading techniques. Multithreading allows you to distribute the workload across multiple threads, enabling concurrent execution and potentially reducing the overall execution time. By dividing the triangulation process into smaller tasks that can be executed in parallel, you can take advantage of modern multi-core processors to speed up the computation. However, ensure that proper synchronization mechanisms are in place to avoid data races and inconsistencies. 11.3.2.3 Spatial data structures. Spatial data structures, such as quad trees or KD trees, can enhance the performance of searching and inserting points within the triangulation. These structures partition the input space into smaller regions, allowing for faster point location queries and reducing the number of comparisons needed. By organizing the points spatially, it becomes easier to find neighboring triangles and perform geometric queries efficiently. This improves the overall performance of the Delaunay triangulation algorithm, especially when dealing with large datasets. 11.3.3 Memory management. Efficient memory management is crucial for optimizing the memory usage of your Delaunay triangulation implementation. Here are some strategies to consider. 11.3.3.1 Object pooling. Using object pooling techniques can help reduce the overhead of memory allocation and deallocation. Instead of creating new objects for each point or triangle, you can reuse previously allocated memory blocks from a pool. By initializing a fixed number of point and triangle objects at the beginning and reusing them throughout the triangulation process, you can minimize the frequency of dynamic memory allocation and deallocation, resulting in improved performance. 11.3.3.2 Memory compression techniques. Applying memory compression techniques can be beneficial, especially when dealing with large datasets. Instead of storing the entire triangulation in memory at once, consider using compressed representations that require less memory space. Various compression algorithms, such as run-length encoding or delta encoding, can reduce the memory footprint by storing the data more efficiently. However, keep in mind that compression and decompression operations may introduce additional computational overhead, so it's important to measure the trade-off between memory savings and processing time. Conclusion. In this section, we discussed strategies to optimize the performance and memory usage of your Delaunay triangulation implementation in 2D graphics using C by carefully selecting appropriate data structures, leveraging algorithmic optimizations, and employing efficient memory management techniques. You can significantly improve the efficiency of your implementation. Remember that optimization is a multifaceted process, and the specific techniques required may vary depending on your implementation and the characteristics of the dataset. It is advisable to profile and measure the performance of your triangulation code to identify potential bottlenecks and areas for improvement. 11.4 Handling special cases and edge cases. In the process of implementing Delaunay triangulation in 2D graphics using C, it is important to consider and handle special cases and edge cases that may arise. These special cases often require specific treatment to ensure the correctness and efficiency of the triangulation algorithm. In this section, we will explore some common special cases and techniques to handle them effectively. Collinear points. One common special case that needs to be addressed is when the input points are collinear, meaning that they lie on the same line. In this case, the standard Delaunay triangulation approaches may fail or produce incorrect results. To handle this situation, a common solution is to add a small perturbation to the collinear points to create a slight variation in their positions. This perturbation helps to break the collinearity and ensures that the triangulation algorithm works correctly. However, care must be taken to ensure that the perturbation does not introduce any significant errors or distortions in the resulting triangulation. Duplicate points. Another special case to consider is when there are duplicate points in the input. Duplicate points can cause issues in the Delaunay triangulation algorithm, leading to incorrect results or even infinite loops. To handle this case, it is essential to detect and remove duplicate points before constructing the triangulation. This can be achieved using efficient data structures such as hash tables or balanced search trees to detect and eliminate duplicates. Once the duplicates are removed, the triangulation algorithm can proceed as usual. Degenerate triangles. Degenerate triangles are triangles with zero or infinitesimal area. They can occur due to various reasons, such as duplicate or collinear points, or when the input points lie on the boundary of the triangulation. Degenerate triangles can cause issues in subsequent geometric calculations, such as determining the circumcircle or checking the Delaunay property. To handle degenerate triangles, special cases need to be considered in these calculations. For example, when determining the circumcircle of a degenerate triangle, the algorithm should handle the case where the triangle's points are collinear or when the triangle involves duplicate points. Adjustments to the regular calculations may be needed to account for these cases and ensure correct results. Boundary constraints and convex hulls. In some cases, there may be explicit boundary constraints that need to be enforced in the Delaunay triangulation. For example, if the input points represent a polygon, it may be required that the triangulation only considers points within the interior of the polygon and ignores points outside. This can be achieved by constructing the convex hull of the input points and using it as a constraint during the triangulation. Points outside the convex hull would be excluded from the triangulation process. By handling boundary constraints effectively, it is possible to obtain the desired triangulation that satisfies the given requirements. Floating point precision issues. When working with floating point arithmetic, precision issues can arise, leading to inconsistencies or errors in the triangulation algorithm. These issues can be particularly problematic when calculating the circumcircles of triangles or performing geometric operations involving small values. To handle precision issues, it is important to use appropriate numerical techniques such as robust geometric predicates or arbitrary precision libraries. These techniques help to mitigate the effects of floating point precision and ensure accurate and reliable results. Boundary intersections and overlapping triangles. In certain scenarios, the boundaries of triangles in the Delaunay triangulation might intersect or overlap due to specific characteristics of the input data. When this happens, additional steps may be required to resolve these cases effectively. For example, one approach is to perform a post-processing step to detect and eliminate any intersecting boundaries. This can be achieved by examining the edges of the triangles and applying appropriate geometric operations to reconfigure the triangulation and resolve overlapping regions. By handling boundary intersections and overlapping triangles, we can ensure the correctness and visual coherence of the final triangulation. In conclusion, handling special cases and edge cases is a crucial aspect of implementing Delaunay triangulation in 2D graphics using C. By addressing issues such as collinear points, duplicate points, degenerate triangles, boundary constraints, floating point precision, and boundary intersections, we can achieve a robust and reliable triangulation algorithm. This ensures that the resulting triangulation is correctly computed and visually pleasing, even in challenging scenarios. 12. Conclusion and further learning. 12.1 Summary of the book. In this book, we have explored the topic of implementing Delaunay triangulation in 2D graphics using C. Delaunay triangulation is a fundamental algorithm in computational geometry that allows us to divide a set of points into non-overlapping triangles while satisfying certain constraints. It finds applications in various fields, including computer graphics, computational physics, and geographic information systems. In Chapter 1, we provided an introduction to Delaunay triangulation, discussing its importance and giving an overview of the algorithm. We also explored the different types of Delaunay triangulation algorithms and their advantages and disadvantages. Chapter 2 focused on the basic concepts of 2D graphics, including coordinates and coordinate systems, basic geometric primitives, transformation and affine operations, and rendering and displaying 2D graphics. These concepts form the foundation for understanding and implementing Delaunay triangulation. In Chapter 3, we delved into the data structures necessary for implementing Delaunay triangulation. We discussed the representation of points, triangles, and edges, and explored efficient data structures for search and insertion operations. These data structures are crucial for maintaining the triangulation and ensuring its correctness. Chapter 4 introduced the incremental Delaunay triangulation algorithm, which is one of the most commonly used algorithms for constructing the Delaunay triangulation. We discussed the initialization and first triangle, adding points to the triangulation, and flipping and adjusting the triangulation to maintain the Delaunay property. Chapter 5 covered different Delaunay triangulation algorithms, including the Bowyer-Watson algorithm, the sweep line algorithm, and the divide and conquer algorithm. We compared these algorithms and discussed their strengths and weaknesses in different scenarios. In Chapter 6, we explored the Delaunay property in detail. We defined the Delaunay property and discussed how to determine the circumcircle of a triangle. We also explained the process of checking if a given triangulation satisfies the Delaunay property. Chapter 7 shifted our focus towards the practical aspects of implementing Delaunay triangulation. We discussed input data preparation, choosing the right algorithm based on the problem requirements, performance considerations, and how to handle degenerate cases that may arise during the triangulation process. Chapter 8 delved into various performance optimization techniques for Delaunay triangulation. We explored the use of spatial data structures, incremental updates, and dynamic triangulation to improve the efficiency of the algorithms. We also discussed the concepts of parallelization, multi-threading, and memory management for optimizing performance and storage efficiency. In Chapter 9, we presented practical implementations of Delaunay triangulation in the form of libraries. We provided an overview of the features and capabilities of these libraries, demonstrated their usage and integration in different applications, and explored how to interface them with other graphics libraries. Additionally, we presented case studies and real-world applications that showcase the power and versatility of Delaunay Triangulation. Chapter 10 covered advanced topics in Delaunay Triangulation. We discussed boundary constraints and convex hulls, Delaunay refinement and mesh generation, Voronoi diagrams and Delaunay duals, and higher dimensional Delaunay triangulation. These advanced topics provided a deeper understanding of the algorithm and expanded its applications into more complex domains. In Chapter 11, we addressed troubleshooting and debugging techniques specific to Delaunay triangulation. We highlighted common mistakes and errors that beginners may encounter and provided strategies for debugging and optimizing performance and memory usage. We also discussed how to handle special cases and edge cases that may require special attention. In this final chapter, we have summarized the key points and lessons learned throughout the book. We have provided a comprehensive overview of Delaunay triangulation, from its fundamental principles to its practical implementation. We have explored various algorithms, data structures, and optimization techniques, and discussed their applications and trade-offs. To further deepen your knowledge of Delaunay triangulation, we have compiled a list of resources for further learning in Section 12.3. These resources include research papers, books, and online tutorials that will assist you in enhancing your understanding and exploring more advanced topics in the field. Finally, in Section 12.4, we have briefly discussed the future trends and developments in Delaunay triangulation. We have touched upon emerging technologies and research areas that are pushing the boundaries of the algorithm and opening up new possibilities for its application. We hope that this book has equipped you with the necessary knowledge and tools to implement Delaunay triangulation in 2D graphics using C. Whether you are a student, a researcher, or a developer, the concepts and techniques covered in this book will serve as a solid foundation for your journey in the field of computational geometry. 12.2 Key Takeaways and Lessons Learned. In this book, we have explored the fundamental concepts of Delaunay triangulation and its implementation in 2D graphics using the C programming language. Throughout the chapters, we have delved into the theories, algorithms, and practical aspects of Delaunay triangulation. Now, let's summarize the key takeaways and lessons learned from our journey. 1. Understanding Delaunay triangulation. Delaunay triangulation is a geometric algorithm used to divide a set of points into non-overlapping triangles. It has many applications in various fields, including computer graphics, computational geometry, and scientific simulation. By understanding the basics of Delaunay triangulation, we can leverage its power in solving complex spatial problems. 2. Types of Delaunay triangulation algorithms. There are different types of algorithms to compute Delaunay triangulation, each with its advantages and disadvantages. The Bowyer-Watson algorithm, sweep-line algorithm, and divide-and-conquer algorithm are some common approaches. By exploring these algorithms, we can choose the most suitable one based on factors such as simplicity, efficiency, and memory usage. 3. Data structures for efficient implementation. Efficient implementation of Delaunay triangulation requires well-designed data structures. Point, triangle, and edge representations play a crucial role in managing geometric primitives. Moreover, utilizing efficient data structures for spatial search and insertion operations contributes to the overall performance of the algorithm. 4. Checking the Delaunay property. The Delaunay property states that the circumcircle of each triangle in the triangulation should be empty of other points. Understanding how to determine circumcircles and how to validate the Delaunay property is important to ensure the correctness of the triangulation algorithm. 5. Practical implementation considerations. Real-world applications of Delaunay triangulation require careful considerations. Preparing input data, selecting the right algorithm, and handling degenerate cases are important aspects to keep in mind. Additionally, performance optimization techniques like spatial data structures, incremental updates, and parallelization can significantly improve the efficiency of Delaunay triangulation. 6. Practical implementations and libraries. There are existing libraries available that provide Delaunay triangulation functionality. Understanding the features and integration of these libraries can save development time and effort. Moreover, learning from case studies and real-world applications can provide insights into solving complex problems using Delaunay triangulation. 7. Advanced topics in Delaunay triangulation. Advanced topics like boundary constraints, Delaunay refinement, Voronoi diagrams, and higher dimensional triangulation open up opportunities to explore the broader applications of Delaunay triangulation. By extending our knowledge and skills in these areas, we can tackle more complex geometric problems. 8. Troubleshooting and debugging. While implementing Delaunay triangulation, it is common to encounter errors and performance issues. Being aware of common mistakes, adopting effective debugging techniques, and optimizing performance and memory usage can help overcome these challenges and ensure smooth implementation. 9. Conclusion and further learning. In conclusion, this book has provided a comprehensive understanding of implementing Delaunay triangulation in 2D graphics using C. We have learned the theories, algorithms, practical implementations, and advanced topics related to Delaunay triangulation. To enhance our knowledge further, there are several resources available, such as research papers, online courses, and additional books, which can help deepen our understanding and explore new developments in this field. By applying the principles and techniques learned in this book, readers will be equipped to leverage Delaunay triangulation in their own projects, whether it's for computer graphics, data visualization, scientific simulations, or any other application that requires efficient spatial partitioning. Embrace the power of Delaunay triangulation and continue your journey towards mastering the art of 2D graphics. 12.3 Resources for further learning. Congratulations on completing this book on implementing Delaunay triangulation in 2D graphics using C. By now, you should have a solid understanding of the fundamental concepts, algorithms, and practical considerations involved in Delaunay triangulation. However, there is always more to learn, and this section will provide you with a list of resources that can further enhance your knowledge and skills in this subject. Books. Reading books on Delaunay triangulation and related topics can deepen your understanding and introduce you to advanced techniques and applications. Here are some recommended books. Computational Geometry, Algorithms and Applications, by Mark de Burgh, Otfried Chung, Mark van Creveld, and Mark Overmars. This comprehensive textbook covers a wide range of topics in computational geometry, including Delaunay triangulation and its applications. Triangulations, Structures for Algorithms and Applications, by Otfried Chung, Jean-Daniel Boissonnet, and Frederick Chazal, focusing specifically on triangulations. This book delves into various types of triangulation algorithms, including Delaunay triangulation, and explores their structures and applications. Geometric Tools for Computer Graphics, by Philip Schneider and David H. Eberly. While not solely focused on Delaunay triangulation, this book provides an excellent overview of various geometric algorithms and techniques commonly used in computer graphics, including many relevant to Delaunay triangulation. Research Papers. Research papers are an excellent source for diving deep into specific aspects of Delaunay triangulation and staying up to date with the latest developments. Here are some notable research papers on the subject. Delaunay Refinement Algorithms for Triangular Mesh Generation, by Su-Wing Cheng, Tamal K. Day, and Jonathan Shuchik. This paper introduces approaches for improving the quality of Delaunay triangulation through mesh refinement, discussing various algorithms and their advantages. Fast Randomized Point Location Without Preprocessing in 2- and 3-Dimensional Delaunay Triangulations, by Otfried Chung, Hazel Everett, and Mark Glissé. This paper presents a fast and efficient method for performing point location queries in Delaunay triangulations without preprocessing steps. Efficient Algorithms for Delaunay Triangulations and Convex Hulls in Higher Dimensions, by Nabil H. Mustafa and Norbert Zay. This paper explores algorithms and data structures for Delaunay triangulation in higher dimensions, providing valuable insights into extending the concepts beyond 2D. Online courses and tutorials. If you prefer a more hands-on and interactive learning experience, online courses and tutorials can be a great option. Here are some platforms that offer courses related to Delaunay triangulation and computational geometry. Coursera. Coursera hosts a variety of courses on computer graphics, computational geometry, and related topics. Search for courses that cover Delaunay triangulation to find relevant resources. Khan Academy. Khan Academy offers free video tutorials and interactive exercises that cover various topics in computer science and mathematics. Their geometry and algorithms sections can provide a good foundation. YouTube. Many individuals and organizations create video tutorials on Delaunay triangulation and related subjects. Explore YouTube for tutorials that suit your learning preferences. Open source libraries and tools. Working with open source libraries and tools can help you implement Delaunay triangulation more efficiently and explore additional functionality. Here are some popular options. CGAL. The Computational Geometry Algorithms Library, CGAL, is a powerful and comprehensive library that provides algorithms for various geometric computations, including Delaunay triangulation. COLCOL is a widely used library for computing convex hulls, Delaunay triangulations, Voronoi diagrams, and other related structures. Triangle. Triangle is a lightweight C library specifically designed for 2D mesh generation, including the generation of Delaunay triangulations. Online communities and forums. Engaging with online communities and forums allows you to connect with experts and enthusiasts in the field of computational geometry. Here are some notable platforms. Stack Overflow. StackOverflow.com. Stack Overflow is a popular Q&A platform where you can post questions related to Delaunay triangulation and receive help from the community. Computational Geometry Mailing List. compgroups.net/compgeom. This mailing list provides a platform for engaging in discussions and seeking advice on various topics related to computational geometry. Remember, staying connected with the academic and professional communities can provide valuable insights, resources, and opportunities to collaborate or contribute to the field of Delaunay triangulation and 2D graphics. 12.4 Future Trends and Developments in Delaunay Triangulation. As technology advances, the field of Delaunay triangulation continues to evolve, opening up new possibilities and challenges. Here are some exciting future trends and developments to keep an eye on. Higher dimensional Delaunay triangulation. Extending Delaunay triangulation to higher dimensions allows for the analysis and processing of volumetric data. Research in this area focuses on developing efficient algorithms and addressing the computational challenges associated with higher dimensions. Dynamic Delaunay triangulation. Adapting Delaunay triangulation to handle dynamic environments, where the input points change over time, can enable real-time applications in areas such as computer graphics, physics simulations, and spatial analysis. Ongoing research aims to develop techniques for efficient incremental updates and dynamic operations on Delaunay triangulations. Hardware acceleration. Leveraging the power of specialized hardware, such as GPUs, graphics processing units, and FPGAs, field programmable gate arrays, to accelerate Delaunay triangulation computations is a growing area of interest. Optimizing algorithms for parallelization and utilizing hardware-specific features can significantly improve performance. Real-world applications. Delaunay triangulation finds applications in various fields, including computer graphics, computational physics, geospatial analysis, and mesh generation. Future developments are likely to focus on improving Delaunay-based algorithms for specific applications and developing new techniques for solving domain-specific problems. By staying informed about these trends and developments, you can continue to expand your knowledge and contribute to the advancements in Delaunay triangulation and its applications. Congratulations once again on completing this book. It is our hope that you will continue your journey of learning and exploration in Delaunay triangulation, 2D graphics, and computational geometry. Keep practicing, experimenting, and pushing the boundaries of what can be achieved with Delaunay triangulation in the field of computer graphics. 12.4 Future Trends and Developments in Delaunay Triangulation. Delaunay triangulation is a widely used algorithm in the field of computer graphics and computational geometry. Over the years, significant advancements have been made in improving the efficiency, accuracy, and functionality of Delaunay triangulation algorithms. In this section, we will explore some of the future trends and developments in Delaunay triangulation. Integration with machine learning and artificial intelligence. One exciting area of research is the integration of Delaunay triangulation with machine learning and artificial intelligence techniques. Researchers are exploring how Delaunay triangulation can be used as a preprocessing step for various machine learning tasks such as image recognition, object detection, and natural language processing. By leveraging the geometric properties of Delaunay triangulation, it is possible to extract meaningful features from complex data sets. These features can then be fed into machine learning models to improve their accuracy and performance. This integration opens up new possibilities for using Delaunay triangulation in a wide range of applications, including computer vision, robotics, and data analytics. Real-time Delaunay triangulation for interactive applications. Another important trend in the field of Delaunay triangulation is the development of real-time algorithms that can handle triangulation on large datasets and provide instant feedback. Traditional Delaunay triangulation algorithms can be computationally expensive, especially when dealing with complex or changing data. Researchers are actively exploring efficient data structures, optimizations, and parallelization techniques to speed up the Delaunay triangulation process. These advancements aim to enable real-time triangulation for interactive applications such as video games, virtual reality, and augmented reality, where dynamic and responsive rendering is crucial. Application in computational fluid dynamics. Delaunay triangulation has proven to be a valuable tool in computational fluid dynamics (CFD). CFD is an essential technique used in various fields, including aerospace, automotive design, and weather simulation. It involves solving complex partial differential equations to simulate fluid flow and predict the behavior of fluids in different scenarios. Researchers are continuously exploring ways to enhance the accuracy and efficiency of CFD simulations by integrating Delaunay triangulation algorithms. By constructing high-quality meshes using Delaunay triangulation, it is possible to achieve more accurate CFD results with reduced computational cost. This integration also enables the simulation of complex fluid flow phenomena with higher fidelity. Delaunay triangulation for 3D and higher dimensional data. While Delaunay triangulation is primarily used for 2D graphics, there is a growing interest in extending these algorithms to handle 3D and higher dimensional data. This is particularly relevant in industries such as computer-aided design, medical imaging, and computational biology. Efficient algorithms for 3D and higher dimensional Delaunay triangulation can enable the generation of high-quality meshes for complex 3D models and volumetric datasets. These meshes can be further utilized for various applications, including surface reconstruction, shape analysis, and volume visualization. Exploration of alternative triangulation methods. Although Delaunay triangulation is widely used and proven to be effective, researchers continue to explore alternative triangulation methods. These methods aim to overcome the limitations and challenges faced by Delaunay triangulation in certain scenarios. One such alternative is the use of weighted Delaunay triangulation, where additional weights are assigned to the vertices to bias the triangulation towards specific criteria. Weighted Delaunay triangulation allows for more flexibility in controlling the resulting triangulation based on user-defined preferences. Other alternative methods, such as constrained Delaunay triangulation and conforming Delaunay triangulation, are also being actively researched. These methods introduce additional constraints or surface constraints to enforce specific geometric properties or shape requirements in the triangulated mesh. Conclusion. Delaunay triangulation has come a long way since its inception and continues to be a fundamental technique in 2D graphics and computational geometry. The future of Delaunay triangulation holds promise with advancements in integration with machine learning, real-time algorithms, computational fluid dynamics, handling higher dimensional data, exploring alternative triangulation methods, and more. As technology advances and computational power increases, researchers will undoubtedly continue to push the boundaries of what is possible with Delaunay triangulation, enabling its application in even more diverse fields and opening up new avenues for creativity and innovation in the world of computer graphics.